I've been working with multimodality in general for interfaces, working for some years with voice interaction, even before Google apps, Google application devices. And nowadays I'm working with hand gestures, also focus on multimodality, but for cameras. Then I'm part of the video tech team for GN.
Hi, everyone. My name is Anuj, and I used to be a part of the Jabra team before I joined Adobe recently. And this was our research that we did across 3.5 beautiful years at Jabra for optimizing our models. My experience has been, I have a master's in computer engineering, and I started my career with Bose in terms of optimizing neural networks for running on your headphone devices and other kind of audio devices. So mostly audio research and deep learning for that, optimizing the models. And then I joined Jabra, where I worked on video collaboration products for meeting rooms and some personal cameras, where my job was mostly taking the models from research to production and everything in between, starting from dataset generation, optimizing the models, coming with architectures with hardware, and looking at the AI models not just as some kind of a software, but looking at the hardware and making it both hardware and software co-design.
Sorry for that, technical problems.
Hi, everyone. My name is Shan Ahmed Shafi. I did my master's at Leibniz University in Germany, and I'm one of the newer recruits of Jabra as a team, and I'm lucky enough to work with these guys over here, and my expertise is more in the audio domain, and we are exploring more into the multimodality as an aspect, and I'm going to be working more into how we can add audio and video together into giving a much better experience in the far end. And we also have a person in the far end who, sorry.
Yeah, because he had problems with visa, but we also have one online colleague here, Narcy. He's online on Zoom. Narcy, please, could you introduce yourself?
Sure. Hi, everyone. My name is Narcy. I'm an AI/ML researcher at Jabra. Previously, I did my master's and PhD from University of Missouri, Kansas City. And during the same time, I worked as a research intern at Zolos, working on mobile biometric applications. And in Jabra, my work mostly started as an edge AI model developer. And right now, I'm working mostly on synthetic data sets and developing synthetic dataset pipelines and testing out different models for different hardwares.
Okay, thanks a lot. It's not able to see you on Zoom? Okay. Let me change. What about now? Can you see the slides on Zoom, Narcy?
I can see the slides, yes.
Yes?
Yeah.
Okay. I don't know why. Okay, then some idea what you are going to see today in terms of learning outcomes. Initially, I'm not sure if everyone has the background regarding to Edge AI, but we're going to give you one overview that at least you can understand what is the concept of Edge AI. Then it's basically practical. If you have experience in developing models and neural networks in general, let's now have another point of view, how to deploy this for small devices. Then this is the concept we're going to introduce for you in the beginning. Once you have the knowledge about this module development, we're going to show to you how to deploy the modules. Of course, like at Jabra products, we have you do not have access to modify the firmware from our products. But I brought for you here this camera, and this camera, for example, it's Luxon's camera, and it has basically the same architecture as our P20 camera. The only difference here, this is open source. You can use in Python, you can use C to get your custom module and deploy directly to the camera. Then basically, you can also implement some interaction directly into the camera. The pipeline is the same. It's because we have a closed firmware but the way that you are going to deploy the model, to optimize and deploy the model, basically, it is the same. Then based on this, we have two case studies. Anuj is going to explain to you how to use the Qualcomm, because some of our cameras use the Qualcomm chipset, and the other one, I'm going to explain to you how to work with the Mediatex that is quite similar to this camera. In fact, it could be quite confusing for you, because all the time you can see in the slides that I have the word GN, and sometimes we call the Jabra. Then do we work at GN or do we work at Jabra? In fact, GN is a big company. Okay, it's one of the biggest company from Denmark, and an old company. I guess it's around 155 years old. And on that time, they produce the communication between Denmark and China. And as you can see, it's a very old company in terms of technology. When we talk about Jabra, in fact, Jabra, it's a small, one of the companies that belongs to GN. We have different brands at GN. And what could be more confusing for you, it is that you know Jabra because the headsets were quite famous about audio. And what are here to talk about video. It could be confused because, in fact, one of our products, it is the Panacast. We bought the company, we bought the company. Does it work?
Yeah.
Yeah? It works? No. Okay. I don't know what happened, but as I'm a teacher, it works now? Okay, yeah. Sorry for that. What I was explaining, okay. We bought a company called Panacast, and now we have these cameras that is called the Jabra Panacast. The P20, we also have this one that has a very wide field of view and more products regarding to the video. Then we here are part from the video department, and our objective is that we could develop machine learning to execute directly into the camera. Then I brought to you this small video that basically show one overview in terms of the video technology produced by Jabra nowadays. Okay, it's very short, then we can start the workshop after this video. Okay, then thank you for your attention. In this opening, let's start by the introduction of AGI.
Thank you, Fabricio. Just a quick raise of hands just to see how many people here have ever worked with the edge device. It could be like a Arduino, Raspberry Pi, anything, or I've heard the terms. Okay, nice. Quite a few people. Nice. How many of you have deployed a model ever on any of these devices? It could be like a fun hobby project, proof of concept, anything.
Yes,
nice.
as well.
Yes. Okay. Okay, awesome. So a lot of you. So in terms of introduction, all of you know that you have worked with some kind of a small device. So what we are going to see is what is Edge AI. A lot of us have heard a lot about the Cloud AI, but let's also see that how Edge AI differs from Cloud AI. What are the components and what are the advantages, disadvantages, what are the challenges? So let's go ahead with that. So in very simple terms, Edge AI is bringing your neural networks and trying to run them efficiently on your edge devices. It could be anything from your smartwatches to your phones, to your earbuds, to your laptops, to your mobile phones, or any other devices. And at the core of this is models running locally, having private compute so that none of your data goes out to the cloud or anywhere else. You have enhanced privacy and security. You have operational reliability. So you are not looking at, okay, my internet went down, my model suddenly doesn't work, most of my features are gone, so everything is running on device. You have energy efficiency because you don't need to connect over Wi-Fi all the time. It's all local, so it can be much more efficient if they understand the hardware. And you have, of course, lower latency, so you are not worrying about how long the latency is from taking the data from your mobile device or from your laptop to the cloud and coming back with the data, because it's all running locally. And Cloud AI, as everyone of us know, it's much more scalable. So I can deploy the same models across the world in different zones. It's much more accessible. You have cost effectiveness there because initially you don't need to buy the hardware. You are basically subscribing that if you're using a software, you're subscribing to some services, or some services are being given to you as a free subscription or something like that. Integration and collaboration is kind of easy because you might be using some kind of an application or some kind of a device. So things might come pre-configured, or the OS developer or the application developer might integrate those features later on for you. So you don't have to worry about where the device is, what different kind of devices are. It's continuous improvement because you can always push a new model and you always get the latest improvements. Whereas as compared to cloud, if we go towards the edge, you have, if talking about just the iOS devices, you have different kind of iPhones which have the Bionic processors. But in Android side, the market is much more cluttered. You have devices that have only the CPU, only a CPU and a GPU. Some have specialized DSPs for accelerating the models, and some have NPUs. But not all devices are the same. So basically, what do you optimize your model for? Do you optimize it just for the CPU, just for the GPU, just for the DSP, or all of them, depending on like which devices would you support? So in terms of just model training itself, if we see the biggest models with the transformers and all, they consume a lot of energy and they have a huge carbon footprint. But this is only floating point 32 model training. What about inference? Of course, we say that the models are kind of smaller. You can reduce the bit width to say int8 or int4. You can have them run faster. But you understand this, right? The training is happening only, say, I did like 10, 20, 100 experiments, my training is done. But then I am deploying the model for inference. It's getting scaled for billions of users who are making thousands or millions of API calls almost every hour or every minute. So over time, this basically scales up as compared to running things on the edge, where you can run as frequently as possible, as energy efficient as possible with low latency. Looking at some of the prominent examples in the market where Edge AI is being used. So Tesla uses Edge AI for running models locally, for detecting where your lane lines are, where your different kind of objects are, whether it's traffic lights, traffic cones, and things like that. John Deere uses that for their see and spray technology for the weed detection. Apple uses that for different kind of things. Delta Airlines uses that for predictive maintenance in airline industry. We, of course, use it in Jabra Panagast 50, Panagast 20, Panagast 50 VBS and other products for smart meeting room experiences. And then NASA used that for the Perseverance Mars rover, which is on Mars. So inherently, the edge devices give you security and privacy. So you have data encryption. Data is not leaving your device. All the inference is happening on your mobile devices or on your laptops. You only get like basic firmware upgrades where there might be model upgrades or basic functionality upgrades, but you are not relying on anything that you cannot see basically if it's happening just in the cloud and you don't even know what happened there. Data is anonymized because you are just doing all the processing on the device. Most of the devices now even come with trust zones where you can encrypt your data and you can have encryption-based inference using machine learning models. And then you're also safe from regulatory compliances, because if you are deploying models in different kind of regions, for example, in Europe, you have to comply with GDPR compliances where you cannot store the data for more than a certain amount of time, or you have to give reasons for why are you storing the data. So it's always better to bring those models down to the device where you can avoid these compliances. So just looking briefly at what are the pillars of Edge AI, what are the main components? The main components look like this. So you have an Edge AI device. One part is the hardware, one part is the AI model, and one part is the software framework, which is bringing all of them together. In terms of just looking at the landscape of the AGI hardware, you have a wide variety of hardware, which could go from all the way from a small Arduino Nano or an Arduino microcontroller, all the way to like NVIDIA Jetson or some other GPUs that you can run these models on. So here are like some of the examples, like Arduino microcontroller, Intel Merid X, Princip Akida, Google HTPU, Raspberry Pis, and stuff like that. Similarly, there are a couple of frameworks that you can use for deploying and optimizing your models. So you have TensorFlow Lite, TensorFlow Lite Micro specifically for microcontrollers. PyTorch has PyTorch Mobile, Execute, Torch, ONNX Runtime. Qualcomm has SNPE framework. Intel has OpenVINO framework. And Edge Impulse is another one where you don't even have to worry about the frameworks. They basically take care of things. So bringing it all together, what does it look like in terms of what are the main steps? If you have a model that you have developed, what are the main steps of deploying it on a device that you want to productionize? So you did the model development. It could be model training in PyTorch, TensorFlow, JAX, whatever framework you love the best. You just take the model weights and the computational graph along with that, and then you perform model optimization on top of that. So you might want to do model pruning, model quantization, knowledge distillation, or other kind of techniques depending upon what your end hardware supports where you want to deploy your models. Once you have your optimized model weights and the model graph, then you can export it to an intermediate representation if your model requires, or if your compiler can directly take these models as it is, then you can just pass them. Once you have your intermediate representation model ready, you just perform model compilation. It could be either from the vendor from whom you have taken the hardware. They have usually the compilers that they provide for doing graph compilation, and they have some kind of performance improvements. For example, they might do kernel fusion, where they might combine the batch normalization layer and fold them into the convolutional layers, or they might do your post-training optimization in terms of quantization and things like that. At the end, what you get is kind of a binary that contains both your model weights and the model graph combined. And you might end up with a file that looks something like a bin file or a XML or DLC or a blob file, depending upon whichever vendor you are using. Once we have this compiled binary, the next step is basically to take that binary and integrate that into your end product. So say if you have a microcontroller and if you're using say C, C++ or any other language there, you basically will take that file and basically it becomes like your small model, which you can just do the inference using any kind of C, C++ code. So you can basically write some primitives where you can just define, okay, this is my input tensor, this is my output tensor. You can pass the input tensor through your bin file or through any of the other compiled binaries, and you will get the corresponding output. The important thing here is to note that you want to just make sure that whatever performance you were getting at the first step, you want to retain the performance as close as possible on the fifth step as well, because otherwise there is a lot of loss in performance. So we'll go through some of the techniques which will help you in keeping that performance while deploying all the models on the edge device. So just quickly looking at what are the challenges, because we talked a lot about edge devices and compared them with the cloud devices, but it should not be that easy, right? So let's talk a little bit about the challenges. Of course, latency is one of the advantages of deploying models on the edge device. And you also want your model to be efficient. They will always be available, and they will always be private. But that also comes at a cost. For example, you don't want a self-driving car having too much latency for a model processing, because if it's running at, say, a certain kind of speed, if the model is running at too much latency, then it could hit another car. Similarly, you don't want certain kind of devices looking for wake words you want them to do the processing as much as possible on the device. You don't want your words and your voice to go on the cloud every time you say a keyword. But in this, the landscape looks something like this, where we have a lot of different kind of hardwares. We have all the way from CPUs, GPUs, DSPs, and very specific deep learning accelerators. So in this, there are two kind of things that happen. As you go from the CPU to the deep learning accelerator, your flexibility keeps on decreasing while your efficiency keeps on increasing. How? If you want to deploy a simple, say, transformer model, if you want to deploy it on a CPU or a GPU, you can do it right now. Like the day transformers came out in 2017, you had the code, you could easily compile that, you can train it, you can do the inference on a CPU and a GPU. But to deploy the same model with optimization on a deep learning accelerator and to get the same inference time and the latency and the memory bandwidth optimization that you need, it took some amount of time. Why? Because they do not have that kind of flexibility, and it's all in the hardware. It's a hardware software co-design problem. It's not only software, it's not only hardware. So you need to support certain kind of layers, like in terms of if it's a int4 quantization, the hardware doesn't support it, the hardware needs to support it before they can even run a transformer layer there. Similarly, in terms of efficiency, the deep learning accelerators are very efficient because they have CNN accelerators or matrix multipliers that are really efficient to do these processing really fast at a very low power constraints. But in the terms of a CPU, if you run the same model for inference or training on your, say, a laptop CPU, it will definitely consume more amount of power. So how does the model inference look like? We talked about the 5 steps about, okay, we have a model, we start from there, we compile the binary, and we can deploy it. So how does it look like in practice? Say I want to perform, say, image classification. I have an input image in CSW format, number of channels, my batch size, height, and width. So basically, I have a compiled model binary, which contains my model compiled graph and the model weights, which have been optimized. Now, in terms of the memory bandwidth, what does this mean? When I'm doing an inference on the hardware, the memory bandwidth comprises of a couple of things. It's my input image or the input tensor that I'm passing. It's my constant model weights that have been compiled into the binary. It's my output and the intermediate activations. And depending upon how much bigger or smaller your input is, your activation size will keep on changing. So these things comprise of your total memory bandwidth. But this is only a small part, right? Because if you are making a system, if you're making a camera system, it's not only a model, it has audio, it has video, it has other things. And audio and video, as you know, have much tighter latency constraints because you don't want the audio to be coming after the video has already arrived, or you don't want the video to come after the audio has arrived, right? So you want all the things to work, and you want to give the higher priority to audio and video, but at the same time, you want to run the model. And if it's a unified memory architecture, where all video, audio, and the ML are using the same memory, so that means you are constrained by the total amount of memory that you have available. So if video and audio are already using a memory, which is a higher priority, then in models, you only have a certain amount of memory bandwidth that you can use. So based upon this, you want to constrain and understand that what your hardware offers and what are the memory constraints and what kind of memory does your model consume in total runtime. So that will be your total runtime memory, your model activations, model weights, inputs and outputs, plus the rest of the things. That's your runtime memory bandwidth. So looking at all of these things, just to go a little bit more into the depth and understanding that what takes it to understand how to deploy models on the edge devices, there is a model. So that's called a roofline model. Let's look at that. So what the roofline model does, it's basically a plot between the operational intensity of your hardware versus the performance that you can get out of it. So basically, number of operations that you have to perform per byte versus the number of operations your hardware can perform per second. And the slope here defines the memory bandwidth that you have. So when you're deploying a model on a hardware device, you basically want to be as right as possible of the inflection point. Why? Say I can assume like I have a processing element which is capable of processing say a single MAC operation, multiply accumulate operation. Now, say I have 10 processing elements, but my memory bandwidth is low. So that means if I cannot get the data to my processing elements on time, my processing elements are sitting idle. So that means I am bandwidth limited. I cannot provide the data as fast as possible to my processing elements. They are sitting idle, so that's of no use to me. Whereas if I go on the other extreme, all my processing elements are fully utilized, but my data pipeline now has to stall a little bit because my processing elements are taking a little bit more amount of time. So what this tells us is that we need to focus on both the memory bandwidth as well as fully utilizing our processing elements. So ideally, we would like our processing elements to be used 100% at the utilization, but that's theoretical. In practical cases, even if you get 60 to 70% of utilization, that's like a really good scenario. So in terms of operational intensity and the performance of the model on a certain hardware, you want to be as right as possible, or at least at the inflection point. And that's where you can say you are fully utilizing your hardware in terms of processing elements and the memory bandwidth, and you're optimizing your models for the certain hardware. So we talked about the roofline model, which gives us the graphical representation to illustrate architecture performance across the different levels of the operational intensity that we can get for a certain model on the hardware. Any questions so far? Ooh, thank you.
Yeah, my father usually say that when we have a lecture and no one asks question, two possibilities. You understood everything or you didn't understand anything. I expect it's the first one. Okay, then this is the first part. As now we have an overview about what is the core of the idea of Edge AI. Narcy is going to introduce you how to develop models. Think about the concepts of Edge AI, okay? I'm so sorry, Narcy is supposed to be here today with us, but regarding to his visa, he couldn't attend. He is in India now. If he has some kind of technical problems, we recorded a video, one offline video, then I can present the video. But I expected everything's gonna work today. Okay, Narcy, can you hear me?
Yes, I can hear you.
And let's change now. I'm going to stop sharing here. If you can share your screen with us. Yes. Now everyone can see your video. Yes, nice. Thank you a lot. Then module development for Edge AI.
Hello, everyone. So for my part of the presentation, I will be talking about mostly like what was our thought process when we are developing a segmentation model during 2021 to 22 for our web cameras, especially for P20 personal web camera. So in this presentation, as an overview, first we'll talk about what was the hardware we used, and then what were the operating specifications we consider for our segmentation model, and what are the limitations and problems we faced during the model designing, then followed by dataset and training procedure, and then we show some video results. So first of all, the hardware we used is MirrorX vision processing unit, and what we see here is a block diagram of the AI side of the system of the chip, which uses the vector processing part. So here, I don't know if you guys can see my cursor, but the bottom left part, you guys can see something called shave processors. Those are the programmable vector processing units, and it has 16 of them. So basically, they're designed in such a way that you can run multiple deep learning models on a combination of these shaves. And another part of this SoC is the CMX memory, which is called connected matrix memory, which is total of 2.5 megabytes, but it is divided into 15 slices of 128 kilobytes. And basically, the way we can use the hardware is we can combine a set of shaves, processors, and slices of memory to perform different operations. For example, we can use 4 of the shaves and 4 of the slices to create a head and body detector deep learning model. And we can use another set of shapes and slices to do any other deep learning model or a vector processing unit together in parallel. Another part of the MirrorX chip is the neural compute engine. It has a set of deep learning layers which are optimized to run on the MirrorX. Secondly, the operating specifications for our model is that when we started this project, we already know that there are some pipelines already existing on the camera. A few of them are the video and audio processing pipelines. They're already using a set of shapes and slices of memory on the camera. And also along with that, we have other deep learning models such as head and body detector, which is running parallelly in the hardware. Because of that, when we decided to add a body segmentation model, we were left with only 2 shapes and 2 slices of memory. So going back, MirrorX advertised their hardware can run at maximum or peak of 400 million operations per second. That means when we ended up with 2 shapes and 2 slices, we have very less amount of compute and very less amount of memory to work with. Because of that, we decided not to go into like a really complex segmentation model for person. Instead, we just decided to go with a simple and specialized segmentation model. In our case, we decided to only work above the body, the torso, and the head. And also, we decided to use the region of interest we can get from the head and body detector, which is already running inside the camera. And at the end, the whole segmentation pipeline should run in real time, which means when we get a frame, get a region of interest crop from it and perform some pre-processing, then run the segmentation model, and then perform any post-processing like background removal or background blurring, everything together should run 30 frames per second or within 33 milliseconds. That means at the end, our segmentation model should be really, really fast. So we started working on model designing, and we faced some of the limitations with the hardware we have. And one of them is that MediaTek, during 2021, we still were working with 16-bit floating point, and that is the only one which is available in the hardware. Another one is the neural compute engine. The thing with neural compute engine, it has a really optimized layers. However, there are only limited of them. For example, when we look at the normalization layers, only batch normalization was optimized. If we want to use any other normalization techniques like instant normalization or layer norm, they were not optimized. So they will run directly on the shave processors, and they execute really slow. So we need to make sure that we are using only optimized layers so that we get the best performance out of it. And next thing is that the MediaTek doesn't support sparse matrix operations. Because of that, we cannot use any sparse pruning techniques, and only we need to depend on structure pruning techniques such as removal of layers or like channels in the convolution layers, which was really difficult to train. So we, along these limitations, there is one more thing we faced during testing out different models, which is regarding the memory. Because we left with 2 slices of memory, which is like 128 kilobytes of memory, which will be used by the model weights and also the features, feature vectors. There is a lot of copy and fetch operations happening between the CMX memory and the RAM. Because of this, we face 2 problems. One of them is the issue with the spatial resolution of the input. Let's say we have an input of 512 by 512 with 3 input channels, and we want to perform a convolution operation on it. We can see that as we increase the number of convolution of channel outputs, the execution time of high resolution input is going up, and it's going up really fast. What we found out is that even though there are less number of channels, the way the MediaTek operates with the memory is it takes a lot of time to fetch data from the RAM into the CMX memory. Because of this, when we have larger spatial resolution, the execution time is higher. So when we have smaller resolution, for example, here we are showing a 128 by 128 spatial resolution with 48 channels, we can see that it's almost performing 10 times faster than 512 input. And the solution we found out is that we can use at the starting of the input of the convolution, our deep learning model itself to use like large convolution with large stride to reduce the spatial resolution as fast as possible and then perform any complex operations on it. And when it comes to output, we can use depth to space operations such as pixel shuffling to get back the spatial resolution. Another issue we found is with longer skip connections.
We had a problem here with the microphone. Give me a second.
Yes.
To see if it returns.
Yes.
Yes. Now we have the microphone back. If you can, yes, restart.
Is it the previous slide?
No, only the
next.
Only, yes, I guess.
Okay. Yeah.
We lost like your last explanation about this slide. Okay.
So especially for this issue regarding the skip connections, what we found out is that usually in segmentation model, we use an encoder decoder architectures for semantic segmentations, which is like a standard, and UNet is the initial original segmentation architecture. Here, what we found out is that during our experiments, especially when there are longer skip connections from input of the encoder to the output of the encoder, the copy and fetch operations for skip and concatenation are taking a lot of time. Here we are showing with like an exaggerated example because we never use this big of a unit in edge AI applications, but we wanted to show the operation times for skip operation and concatenation operation. And as we can see that as the feature size increase, the execution of those operations also take time. So the solution we came up with this is that whenever we have a long skip connection from input to output, we try to use a simple one-by-one convolutions to reduce the feature size. So the storage, the execution, like the memory size would be smaller. So copy and fetch operations will be also faster. So overall, in our model designing, whenever we want to make our model, we want to make sure that the layers are available in neural computing engine so that they are optimized and run faster. And then to reduce the issue with the memory for spatial resolution, we use large kernels and large stride convolution layers and pixel shuffling at the output for that. And for reducing the memory footprint, we used smaller feature sizes. And also whenever there are longer skip connections, we used one-by-one convolutions to reduce the feature size. And through our research, we tried different convolution blocks, like we tried ResNet block and MobileNet blocks and DenseNet blocks. And during this time, during 2021, a paper published on BiCNet for semantic segmentation, where they proposed a short-term dense concatenate module. And we used a modified version of that in our model. At the end, this is a model we stick with. On the left side, we see our segmentation model, which has encoder and decoder block. Unlike UNet architecture, in decoder, we did not extract features at each layer of the decoder. Instead, we found out that simply upscaling the encoded features and combining them and performing a small amount of convolutions on them, we were able to extract good enough results. And secondly, we can see that what we talked about using a large strided convolution layer at the input of the encoder and pixel shuffling at the output to reduce the spatial footprint. And then we use the one-by-one convolutions to squeeze the features whenever we perform the skip connections. At the end, we were able to end up with a model size of only 300,000 parameters, and were able to run the whole model on our 2 slices and 2 shaves at 18 milliseconds. So we have the model, we need the data set. First, we started with collecting as much as data we can from the real, and we did an in-house data collection for a single person with our personal P20 cameras with different poses, lighting conditions, any occlusions like wearing a face mask or like a long beard, headset, and everything. And this work was mainly done with my ex-colleague. His name is Haris Jilani. He worked with the company to collect the data and did some initial processing on it. But no matter what, it's really difficult to collect a large amount of real data and also annotate it. So we decided to also add our own synthetic data set to the pipeline so that we can increase the overall training set. This work was done by me, and we used a bunch of 3D models we bought and combined and simulated everything in the Blender to generate different poses for the person. During our training, one thing we found an issue is that if we just simply combine all the real and synthetic data sets together and just train, we have really a lot of issues with flickering, or like sometimes it doesn't even segment the person. So we started playing with distribution of real and synthetic data for each batch. At the end, we found out that using like 30% real data and 70% synthetic data in a batch, and then performing a bunch of augmentations on it, and for training, it actually gave us pretty good results. And for training, initially we used self-supervised learning technique Dino just to have some pre-trained weights. And then we trained the model on our training set for almost 10,000 batches. And what we see here is an ideal condition of how the model operates. Like it gets a region of interest crop and it's above the waist, and only the person is in that. And right now the model runs on hardware at 18 milliseconds. And one more example we're going to show is like for when we use the full frame from the camera instead of using just the region of interest. Here you can see that as we trained only on the single person training data, we have some issues. Like, for example, if a person comes into the frame, you can see that it has difficulty blurring out immediately. And sometimes there are like trees and objects like that, they come into frame. So yes, this is our model, which we worked initially around 2021 and 22 to develop it for our hardware. And this is, I hope I provided some examples of how we thought through our experiments, like when we prepared this model. And if you guys have any questions, please let me know.
Sure. Narsi, we have some questions.
Yes.
Okay.
Segmentation, was it Dino or unit that was used? Was Dino used for feature extraction and then unit, the features are fed to unit, or what was the architecture?
Okay, so the question is for the segmentation, was it the Dino or the unit model? And if Dino was used or unit was used, how was the training? Like, what was being trained and what happened where? So, Narsi.
So for Dino, we just replaced, I think Dino was initially using VIT. Like Dino uses a single model for as a teacher and a student. So in our case, we did the same thing. We just used our own model as a teacher and student for training. And when we did an experiment with image classification, just on the self-supervised model at that time, the performance went from like 13% accuracy at top 5 to 60% accuracy at top 5 like detection.
Yes.
Do you have any exhaustive list of things that we should check out within the processor while training the model? These are the things that you look at. In the architecture that he showed, that there was something do we have any exhaustive list for any processor?
So, Narsi, any exhaustive list for the processor to check out before like optimizing the model for running, like how you did that?
I can go into what we did. We started using NAS as an initial experiment where we tried to see if existing NAS architectures can work. And we had a difficulty coming up with the model using that. So we just said, screw it, just brute force and create an Excel sheet of all the layers and all the activation functions and anything we can, and just try to loop it through our hardware to see if we can find any information. And through that, what we found is that the memory issues, especially, and that's how we found out, oh, we know that there is some memory issues on this hardware. So what kind of models we can look into? That's how we try to limit our search in terms of what kind of experiments we can do.
Yes. Yeah.
Just a follow-up question, like based on the problem, how do you decide which kind of
So the question is, based upon the hardware, how do you decide, like, based on the problem, how do you decide which hardware to use? So for our case, I think hardware was already pre-decided.
Yeah, we did not have an option for that. We came into the, we already have the hardware, and they asked us like what we can do it with that.
Yeah, if we had an option, we would have
oh yeah
gone with a different approach, maybe. So this camera was already in production, and then we came in and we started doing the optimizations.
Sometimes we have a fight with the engineer team. These guys optimize the models, and we send to the engineer team. And we have different shades available, the shade is used. And it's always a fight. Okay, you give me one more shave for optimize. No, because we can reserve the shade for another application. Then the hardware is predefined. This is the hardware. We must work around the hardware. But the idea is, if we start implementing many models that it cannot be supported because of the limited number of shapes available. But in the P2M or in the Panacast or the P50, what we could like improve it, provided to the user different firmware. Then if you want to get correction, you can download the firmware. If you want to route segmentation of the firmware, but can you see that in terms of usability and user experience, this could be quite difficult because it's not all the users could be able to download a new firmware and deploy into the camera. And we can also start to have several problems with the customers. Then the hardware is this one, and we should work around the limitations provided by the hardware and everything that is available is still in terms of resources.
Yeah, so a fun story around this is basically if you see what Narsi presented in terms of shapes and slices. So if the processor has 6 shapes and slices, so what Narsi got was only, I think, 1 shape and slice to work with. So you can think of it as like maybe you are getting just 1 or 2 CPU threads and a GPU thread, something like that, to work with for running this, but you still want to run it as efficiently as possible. So again, it's a trade-off between accuracy and latency and accuracy and memory bandwidth, just as Narsi mentioned. Thanks, Narsi.
Thank you.
One more.
Oh, okay, we have one more question. Yes.
Trying out different architectures. Do you train the whole model and then to figure out the accuracy and the latency, and then you do another round and basically do the full training for each variant and then compare the plot the most balance.
Okay, so Narsi, the question is like for figuring out like the latency, memory bandwidth, and like which is the best model, do we train the whole model for all the different variants that we are trying and then figure out the latency, memory bandwidth for that, or do we have a different approach?
We know that we already have a limitation with the hardware and the execution time. So whenever what we do is that we do a literature review of all the models we find. We try to create like a abstract model of what we can run on the hardware, and if we can see that we can run it around 20 milliseconds or faster, then we start training the model on that and see if we can get a good results out of it. That's usually how we work on it, because we already know what was our hardware and what the limit we have on our hardware. So we just take the models, run it, and if it doesn't perform, doesn't run faster, we just move on with the architecture.
Okay, we have a couple more questions. Yes.
Like you mentioned as well, and as well just in presentation that the edge device has limited compute, limited memory.
Yes.
So you cannot put everything on it.
Yeah.
Did you guys experiment with the hybrid kind of an architecture where you were doing some processing, pre-processing on the edge device, and then you offer the more expensive compute task in the cloud architecture?
Okay, so we did not, because I can answer this, I guess, or unless Narsi, you want to take this?
No, you know better on this.
Okay, so the reason being at the core of all our products is user privacy. We don't want to send any data. We don't collect any data. Even if you see those devices, this device, any other device, you can turn off the Wi-Fi and the internet. You can run them yourself. All the compute runs on the device. Nothing leaves the or goes to the cloud. It's being powered through that USB. Or for the bigger devices, they are being powered through like the plug-in socket. That's it. So that's one of the reasons we don't do any kind of data collection or anything, and we did not want it to go hybrid. Of course, that's one of the approach that we could have taken, and we could have run into like multiple bigger models. That's one of the reasons. Second reason is we are latency sensitive, because for our use case, if we are running in a personal use case or a meeting use case, the people are moving all the time or people are talking all the time. We want to look at those things and respond as fast as possible. So given the latency, additional latency that might be there for hitting the cloud and coming back, that was not simply possible. So these are like a couple of reasons for that.
May I add just one information? Privacy is so important for us in Jabra that if you imagine, we have probably the best source of collecting data. That is the camera. We somehow could collect the data from you guys, and they have the best data set in terms of the world, because most of our customers are companies. We also have for big metros, and we could collect the data and work with not only image, interaction in general. We could see human perception. I could have body movements, hand gestures for Elizabeth. but it's so important that we never touch on the data from our customers. That we don't have access to the video stream that comes from you. Because of this, we always think about how to process this in the camera and even the things of background, because most of you probably using Zoom, use Teams for virtual and hybrid meetings, and probably you enable the background segmentation. But the video that came from your webcam and going to the computer, the operating system or third-party application couldn't have access to the background. When we measure that we're going to execute the background segmentation directly to the camera, the video stream provided to the computer, it's without the background information.
Yeah.
Then privacy is the key for our team, and we never touch the video stream from our customers, and we always try to protect you in terms of video and especially in terms of privacy.
We had couple more questions. Yes, please. Anyone can.
Don't worry.
We have time. Yes.
We have plenty of time to answer the questions.
Oh, like you mean like open source code for the models? So these are all, so the question is like, do we have any open source code or anything for these models? So these are all proprietary models with the data set. And like the gentleman also mentioned in one of the workshops, it's not about the models nowadays, it's becoming more about the data set. And that's where the core is. Like we have our own pipeline of synthetic data set and all those things in-house. So yeah, the models are not available. Everything is available just on the device for inference. Okay, Narsi, the question is size of the dataset for Dino pre-training.
I think it's just a scratch of 20,000 images. We randomly collected like greenery. There is no human in those data. It's just like objects and like trees, mountains, and all this stuff. Just to create some randomness in the, instead of having some random weights, just creating some weights in the model.
Yeah. So yes, so Dino is basically what we are doing is instead of training the model from scratch, we are basically using Dino to pre-train the model weight so that it knows something about how to extract features and these kind of things. After that, our data set that we have collected is a combination of real and synthetic data set. That's where the 10,000 batch size number comes from. That's what it comes then after that. Yeah. Yes, please.
So the camera itself has some kind of models running inherently. Did you guys try to experiment with like an end-to-end model which you can optimize? Could you optimize those models running on the device for head detection and body detection?
Yes, so we have optimized, but could you expand on what end-to-end means?
Rather than you using their ROI provided by them and then do segmentation on that?
Provided by who? We are providing the ROIs.
I thought the camera itself was.
Yeah, so it's our camera. In the camera, how the stream works is we get the entire full field of view, whether it's 180-degree in these kind of cameras or whether it's 90-degree or configurable in those kind of cameras. Based on that, we run our person detector and other kind of models. From there, we get a region of interest that where the person is. And then based upon that, you can either run segmentation on region of interest or the full field of view. So it's an end-to-end pipeline basically in that.
Different hardware.
Yes. So for Panacast 20 and this camera, we had a Myriad X, Intel Myriad X. For the Panacast 50 VBS, we have a mixture of Intel Myriad X and a Qualcomm SoC that we'll talk about in the next talk. Yes, please. Sure. Narsi, can you expand a little bit more on the synthetic data set, like how big it is and what were the challenges and what challenges you are facing even now with that?
Synthetic data set, I think we limited it to 50,000 images or something at that time. Challenges is basically I have no clue about 3D modeling. That's the biggest challenge. I don't know why I took up that initially when I did, because I just saw Python in Blender. I'm like, oh, cool, there is Python. I can try something. And that's how it started. And I think at this point, I was able to develop a pipeline for Blender, and I was able to generate a lot of data. But the issue we ran into with that pipeline is that whenever someone else tried to install it in their hardware, it doesn't work properly. Example is Anuj. We tried to set up on his system and it did not work, but it's only working on one system. Initially, we started like that, but now, like this year, we moved away from Blender to Omniverse. We don't have anything yet to share on that, but we have good start in terms of what we can do in Omniverse.
Yeah, I also have a couple of stories around that. So some of the use cases that we were seeing was some of the models would detect like misdetections or would not perform well on segmentations. For example, if I have my hands up or hands behind the head. So in those cases, it was kind of a challenge. I remember Nasi was working with that, and we were trying to get the hands in the right position, but sometimes it will go like this, or go just like in a different direction altogether, not usable. So another thing is like most of the models are like frame based. Like generally models are trained on just individual images. But since we are working on video based, there is a temporal aspect as well, which actually helps in stabilizing whether it's like object detection in terms of bounding boxes or even segmentation maps and things like that. So for that, you need to now generate video frames and not just the image frames, because image frames alone won't work. So there is a time dependence and time continuity that's required there. So there have been like a lot of challenges that we have been going through in terms of synthetic dataset generation. But now, as Narsi mentioned, we are moving a little bit away from that. So hopefully that will help. Let's see. Yes, please. So video frames basically mean like if I am training a model on independent images, for example, let's take a simple example of say image classification. If I want to train a model for image classification on ImageNet, I'll take the ImageNet dataset. Those images are separate individual images, right? They don't have, for example, for a person detection or person classification, they don't have the same person across all the frames. But if I record a video of myself using one of the cameras, I am consistently in the frame. So from each frame to frame, if I'm moving around a little bit, there is that temporal aspect that's coming in terms of detecting me as compared to just taking my individual frames when I'm standing here, there, or somewhere else. So you are missing that temporal aspect. Like, how did I go from here to here? It will miss that if I'm just capturing images. But if I'm capturing videos, so then it knows that these are the steps that he took to go from here to here. So in between, I can then use some layers like COM-GRU or LSTM or those kind of layers that can capture that temporal aspect along with the normal convolutions or normal transformer layers. And that actually helps to smoothen out the bounding boxes or the segmentation maps in the background. Because over time, it knows that if the person was here in 1 second, the person did not disappear the very next second. The person is still there. So it helps to stabilize those things. So Narsi, are we using any temporal layers in our model or in post-processing?
Like in the final model we developed, we used a convolutional GRU at the end of the encoder block. That's the only temporal layer we were able to add, because temporal layer adds another complexity, like adds more parameters and more operations per unit. So we just decided not to use a lot of them, and like one simple convolutional GRU, that's what we used.
Yes.
Implementing the temporal component into the network, did it cause any additional strain on the hardware when you were running the input? Or you had to do something special to make that temporal thing work?
So Narsi, the question is, did we had to do any additional thing or challenges to add the temporal thing and then run it on the hardware efficiently?
Mostly the way we needed to run was the hardware doesn't support memory, like it doesn't save any memory. So we actually needed to just create like a separate variable where we copy the output of the GR unit every time when we run a new frame. Other than that, I don't think we did any additional stuff.
Yeah, but just using the LSTM itself does add a little bit more to the memory bandwidth, because now until you reach the output, you still have to maintain all the intermediate steps for all the time steps. So that's additional memory that you have to keep in mind while adding that. That's why only like one layer in there, and that too, like instead of normal LSTM, you can use like a convolutional GRU or something, so that you can use best of convolution, little bit of GRU, a mix of that, and still get the temporal stability. Yes.
What was the main roadblock that made you give up? Like, was it the time you were saving and then what to break from the hardware and F5?
So what was the challenge of using NAS basically for like, was it hardware in the loop or taking too much time or not having good architectures? What happened?
I think at that time, the hardware architectures we were trying out initially, like before we did the brute force experiment, initially we tried all the known architectures, which are like mobile NAS or like mobile net architectures. We tried using those, but still at the end we were unable to like run the model on real time in the camera on two shapes and two slices. That's the main issue. But I think when thinking back now, once we did the brute force, we know what kind of layers work and what kind of architecture works. Maybe if we go back again to NAS and try it out, we might find better model probably.
Any other? Yes, please.
Make it yes.
Okay. So Narsi, 1 second, let me just share the slides. Narsi slides.
Nas, can you share again your
Narsi,
screen?
can you share the slides and go back to the training pipeline?
Sure.
Also, we can make just make it available in slide.
The training pipeline. Yeah.
These are the only two slides.
Yeah, yeah, yep. Anything else? Yes.
So you mentioned that having temporal applications helps the work. So how did you train your network video and static images?
Yeah, good question. So the question is, how did you train the model on both static images and the video data to add the temporal aspect in there?
Oh, so when we added temporal component to our model, we have two sets of training. In the same iteration, first we get a set of batch of images for which are like single frame data, and we just train the model on that for few epochs, and then we slowly add more video data into our training. That's how we did the training. But at the end, we have both single frame and video data, but the weightage is added more onto the video data so that the temporal unit, the convolutional GRU, can learn on that.
Yes.
So does that mean for the static images, did you freeze the viewing when training?
So for static images, did you freeze the GRU while training with static images?
No, I don't think I freeze. We just ran it as it is. Oh, do you mean like, yes, like during the first epochs when we don't have the temporal data added to the training? Yes, we did not train the GRU unit, but once we started adding the temporal data, we started training the GRU unit. Even like at the end when we add the video data, we still have the still images, right? At that time also the GRU unit weights are trained.
And there's like another second approach, which is like you can train your entire model with the images first. And then if you have video frames, then you can specifically train the GRU itself, the layers for that. And you can keep it frozen for that time. So that also. Okay, so it's time for
Just a second.
break.
Yeah, then Narsi, thank a lot. Yes, thank a lot for your presentation. Let me see here. What do we have? In fact, it's a break now. Yeah. Okay, then it's time for a break. In fact, Thank you a lot for the questions. This is the way that I like to have lectures and interact with my students. Then with you, it was an amazing section. Let's see, I'm gonna give you a bit more than half an hour. We will start again 3:45, okay? Then we can continue with the module deployment. Thank you a lot for the moment. See you in half an hour. Yep. I'm gonna stop here recording.
I was thinking we could have like done it till 3:30 and then start from there and get more time there.
Yeah, because of the I asked you before. You said it's half an hour.
Did we say if anybody wants?
Okay, let's restart. Can you hear me? Yeah. Then now, it's gonna be in two parts about the module deployment for Edge AI. Then we will start with Narcy, explain how to deploy modules for Qualcomm. Then the second part, I will explain to you my experience in terms of deploying modules for Mediapipe. Okay, then let's start. Sorry, I said Narcy.
That's
You are
okay.
twins, guys.
I wouldn't mind. That's okay. Thanks, Fabrice. Okay. I hope everyone is still good and with us. Okay. So model deployment. So far, we have looked at what Nasi talked about in terms of segmentation model, what all challenges he had to face, how he developed the model. But there are a couple more steps that you can look at from a general sense. So I would like to take you through a little bit of the model journey of how things work in terms of a normal general pipeline, all the way from developing your models, doing neural architecture search and things like that from a very high level, and what you can expect in terms of the performance improvements. And then going deeper into step-by-step what other things you can apply on top of that. And then finally looking into two case studies, how we deployed models efficiently on our devices. So here's the agenda. We'll look at model compression techniques. We'll try to define some key metrics so that we can look at each of the compression techniques and compare them in terms of performance and other kind of things, that how we are doing with them, like what kind of things do these things offer? Otherwise, what's the use of just talking about just a compression if we don't have any metrics to compare them on? Then we'll talk about the case studies and a summary. So in terms of model deployment for Edge AI, model deployment is a critical phase because you have now trained your model using PyTorch, TensorFlow, any kind of framework. Now you want to optimize your model, you want to deploy a model, but it's not that easy on the edge as compared to maybe on a CPU or on a laptop on the GPU. That's where you need to compress your model, because these devices, as Nasi mentioned, don't have too much amount of memory and compute and other kind of resources to run them efficiently. If I want to run a big model or train a big model or do the inference of, say, a transformer model, I can easily push it onto a CPU or a GPU. It will still sweat a little bit on the CPU. On the GPU, it should be pretty much okay, given that I'm running with, like, say, int4 quantization or maybe with half precision at floating point 16 or something like that. Should be totally fine. But when it comes to an edge device like the Intel Mirror X that we showed, or Qualcomm device, or even your phones that you have in your pockets right now, it becomes really challenging because these devices are running your entire operating system. Let's talk from a phone perspective. Say, for example, it's running an entire operating system. There are certain processes that are happening in the background. There is audio, video, co-processing systems and other kind of things that are working. And then model and the other neural hardware becomes a very small part of it. And that too has to run multiple models for giving you multiple different kind of experiences. It could be running in parallel. It could be running sequentially, depending upon how the pipeline has been implemented. So model compression becomes really, really necessary, where you can deploy on a CPU or a GPU model, which could be like, say, a couple of megabytes to maybe like gigabytes. On edge devices, you might be limited to even like, say, kilobytes or to 1 megabyte or a couple of megabytes, not more than that. So that's where model compression comes in. The model compression is basically, in brief terms, the art and science of making an AI model that you have trained to run efficiently on a small device, edge device, but without losing the performance. So it's not like you have made a big model and you want to compress it, but then you say that, okay, it's not accurate enough. For example, if I had a good object detection model, it works pretty well when I trained it at FP32, but now I want to deploy it at FP16 or int8. It doesn't work equally well, but I am getting really great latency. That model is of not much use to me because if it has ton of false positive, false negatives, that model I cannot deploy in production. So this is where we'll try to figure out that what are some of the key metrics on which we can compare all of the optimization techniques, and we'll talk about some of them. So here are some of the key metrics that we look from a both hardware and a software point of view, because it's a hardware software co-design problem. We'll talk about size reduction. Of course, size reduction is important because the model, as I told you before, in terms of a single inference, model weights, model activations, inputs and outputs, that comprises of the runtime memory bandwidth that you need. So size reduction is important because your model size goes down, so you use less amount of memory. Model accuracy is equally important. You want a good, accurate model. You don't want a model that's run faster but is of no use at all. Model throughput, the amount of processes that you can do using your processing elements, basically the amount of processing that you can do or number of inferences you can do in an inference point of view that you can do per second. So that becomes kind of your throughput. Power and energy consumption, because if your model or your hardware is kind of like, say, a bigger GPU kind of a model, there you have to have bigger heat sinks, because the more amount of power it consumes, the more number of tops it has, your thermal design for power actually goes up. So it will dissipate more amount of heat. In these small kind of cameras, if they become too hot, they'll just stop working. Memory bandwidth, as we talked before, and the latency, because all the things need to run in a certain time frame. For video and audio, all the things need to run within the 33 millisecond latency limit. They cannot go beyond that. And if a model is a part of the video processing or the audio processing pipeline, it cannot delay the entire end-to-end latency just because you are running a model and you were trying to give a new experience to the customer. The customer doesn't care. So we'll look at a couple of primary techniques that we were able to use through our time span for different kind of models, spanning from segmentation models to object detection model to pose estimation to gaze estimation and other kind of things. In a general sense, what are the techniques, what the landscape looks like, and what kind of performance you can expect out of them, improvements that you can get out of them on the key metrics. So the very first one is neural architecture search. You are beginning from, maybe you already have a model, you are trying to design a model. So first thing, if you understand your hardware well, you know what kind of layers it supports. For example, if I have a MiriDX, it has a CNN accelerator. If I know it cannot support transformer layers, I'll try to avoid them. I'll try to figure out what are the alternatives. Maybe it accelerates CNNs better. Maybe it consumes a lot of memory, like how Narsi mentioned, for the skip connections, it's consuming a lot of memory. Try to reduce my channels. So these, all the things that I'm talking about, these all come as part of your neural architecture design. Before even making a model, you can just figure out using these latency constraints, memory constraints, or whatever key things that you're looking for. You can look at them and you can figure out, okay, these are my minimum and maximum constraints that I can play within, because this is what my hardware supports. I cannot go beyond that because it's of no use. You'll be just redoing the efforts. So given that you have, say, a search space where you know, okay, convolution is a good layer, ghost convolution is another layer that my hardware can accelerate. I can have maybe depth-wise convolution that are faster. Maybe I can have partial convolutions, different kind of things. So these are my layer levels. In terms of kernels, okay, 7x7 works pretty well. 5x5 is good. 3x3 is good. Maybe rest all don't work, so I'll have this as my search space. In terms of maybe the depths, I can go, okay, 32 is good. Like in terms of the width of my layers, 32 is good, 64 is good, 128, maybe 512. But depending on how far close I want to be, I don't want too many features. If it's causing me too much trouble for memory copying, in case of unit, for example, then I'll try to limit it to, say, 64. So once you have a search space, you can use like a controller. It could be like a reinforcement learning algorithm. It could be genetic algorithm that you can go through, and then it will reiterate through all of these things, and it'll give you a architecture, initial architecture. Now, there are two ways. One is that you can look at all the layers and you can look at the latency of layers individually, and you can figure out, okay, these layers are run at this runtime. A combined model might give me certain amount of runtime plus and minus some amount of time. So this should be a good enough architecture. Or second is you can have a model that you get out of that, and then you can have hardware in the loop and you can get your latency estimates for the entire end-to-end model. then maybe you are not happy with the performance of the model in terms of accuracy, in terms of the latency, in terms of memory bandwidth. So here we are working with two different kind of trade-offs: accuracy versus memory bandwidth, accuracy versus latency. So maybe I'm not too happy. Maybe I can optimize a bit more. Maybe I found a new paper that came up with some new kind of techniques, new kind of layers. Maybe I can play some kind of kernel tricks here. So I'll try to go back and reiterate, maybe change my search space and come up with more architectures. So I can reiterate over this process. Once I have a final optimal architecture, I can then go ahead and I can do some kind of more optimization on top of that. So in a very broad sense, these are some of the key on these key metrics. These are some of the values that you can expect in terms of size reductions, accuracy, power and energy consumption, memory bandwidth. Of course, these things can change depending upon what your hardware supports and what kind of layers you choose. But in a very, very broad sense, general sense, these are some of the things that you can expect. Another technique is, so far we have been developing the model, say for an image classification model. What we usually do, we have an entire backbone and we wait for the final layer to give us an output. But what if the intermediate layer has already learned some information that might be useful to make a classification or give me a result as it is at that point itself? Because say, for example, my background for an image for a person detector is not complex enough. It's pretty simple. So my model is able to give me the output, say, on the third exit itself. I don't need to run the entire model, because when I'm running the entire model, say if I'm giving an input image, I'm getting the final output. That means I'm calculating activations for each of the layers until the final output. What if I get output only at exit layer 1? That what means I was only able to calculate the activations for first convolution, second convolution, and the exit layer, and that's it. I don't even need to process the rest of them. Depending upon what's your accuracy requirements, you can provide accuracy thresholds for each of the layer, and you can get a good amount of result right there. So this is another kind of optimization that you can do at the architecture level itself while you're designing your networks. So in terms of early exits, you can have some of these things where you have reduced latency depending upon which kind of exit has been taken. You have lower energy consumption as a effect of that. And then you have adaptive computation depending upon how complex or easy your scenario is on which you are doing your processing or input is. So just to wake everyone up after lunch, let's see a small demo video of how this thing works in action. Okay, so what just happened here, we saw this architecture. This is the exact same architecture that's doing an inference. It's basically a very simple classifier saying whether a human is present in a scene or not. So what you saw in the video is actually at some point of time, if the background was simple enough, it was taking exit 1 or exit 2 rather than going through all the model, like through the final exit. So what this means is my model performance was good. My confidence was 98, 99%, which is way above my threshold of 90% that I set for each of the layers. But at the same time, I reduced my amount of computation and memory bandwidth that was required for me. So this is a very simple use case, but this is basically a similar concept that you can use across segmentation, object detection, and other kind of things in your backbones. Now, looking at early exits, here is another example on the videos, just to understand a little bit deeper on what happened and why it made a certain decision. So we just visualize the activation maps using GradCam. So for all of these images, you can see the confidence of a human presence is 92% with exit 2, 93% with exit 2. For last one, it took exit 4 with 95.9%. Reason being, in exit 4, you cannot see the human's face. Maybe the model actually tried to look at all the features of the human face to make sure that the person is present or not. Plus, the person is a little bit farther as compared to others. And the scene is not too complex, but still it's comparatively different than what it might have seen. And here are some of the activation maps that it saw. So for exit 2, it was able to see the faces clearly. And it was like, okay, I'm sure, 98% sure. Yes, take exit 2, I'm done. I have my confidence. Similarly, for others, exit 2 and exit 3 were kind of pretty good. But in the rest of it, you see that it took it about exit 3 and exit 4 to be more confident and say that, okay, I'm now more sure that there is a person present in the scene and it's not empty scene. So overall, in terms of key metrics, these are some of the values that you can expect to have. Another new technique that's coming from the scenario of large language models is mixture of depths, which is equally applicable to our convolutional models or normal small models, which helps us to, again, have dynamic computation. So that is called mixture of depths. So this is like a architecture from recent paper by Google called mixture of depths, where for a transformer model, they have dynamic compute allocation. So what they have is, given the importance of a token, you can either pass it, if it's too important, you pass it through the entire self-attention layer and multi-layer perceptron. If it's not too important, you can just bypass it through the other layer. So the core of this is the routing layer that's right there. In a very general sense, if you want to design it using, say, a convolutional network, what you can do is maybe have a convolution layer with a linear layer that has softmax as output, as your input to the model. That softmax, say, gives you only two probabilities that take the exit or take the entire route. Based upon that, you can compute the things, and you can actually learn during training that if the input is important enough or the token is important enough to pass it through the entire model or just skip it altogether. And this again gives you dynamic compute allocation. So in this, you have computation savings, and it also provides you with a static computational graph. And again, on the key metrics, you can have some of these numbers that you can achieve. So we talked about neural architecture search, early exits, and mixture of depths. Another technique that's there is hardware-aware design. So we have talked a lot about since the afternoon that you need to understand your hardware, because it's a hardware-software co-design problem and not only a software or a hardware design problem. So what this means is that if you know that normal convolution layers that I am using for doing, say, inferencing or making a model and using them during inferencing, they might be consuming more amount of memory. Also, we know that in convolution, most of the filters contain redundant information, which is that most of the filters might look the same. So is there any way that we can reduce that amount of memory consumption? Because you have to store those filters. So can we reduce that amount of memory and compute consumption? Because you have to compute all of those filters. Can we do that? So one of the concept comes from this paper, Run, Don't Walk, which is called partial convolutions, where instead of running your convolutions across all the feature maps, you have a strategy where you select only certain number of feature maps and you copy rest of the feature maps that you have computed. You apply the next convolution only on that selected set of feature maps and then concatenate the rest of the feature maps as it is. So here you reduce the computation and the runtime memory bandwidth because you only did the compute on a certain number of feature maps that you extracted. Similarly, as Narsi also mentioned about pixel shuffle and unshuffling operations, instead of using in terms of upsampling or downsampling using transpose convolutions, which actually have a lot of compute, you can use pixel shuffle or unshuffling, which basically is a rearrangement operation, which does not cost you too much amount of compute on the hardware. Similarly, one paper from Apple that came out some time ago, Mobile One, sorry. So that paper also follows the same similar techniques, and it shows that how you can design neural networks if you understand your hardware well. And they were able to run their models on an iPhone 12 within 1 millisecond for normal classification problems on ImageNet. Another design, again from an Apple paper called FastVIT. So we all know vision transformers are heavy because self-attention has a polynomial time complexity, and then also because of the feed-forward network that's right after that. So all of those combined make it more computationally and memory intensive. You want to reduce that complexity, but you cannot remove those layers. But instead of that, if you want to use some kind of like convolutional layers, what you can do, you can over-parameterize your model during training. So most of the models that we train are over-parameterized because, as we have seen from the papers that do pruning or lottery ticket hypothesis, is that in the bigger model, there are multiple smaller models that can actually perform at a similar or better level, and you don't need all the weights. So what this basically does is uses a reparameterization trick where during training, you over-parameterize your model. During inference, you can actually combine all the parallel convolution layers that you had in the branches, and you can represent all of them using a single convolution layer. And it still gives you the same performance while reducing amount of compute and latency and memory bandwidth during inference. So in terms of performance, again, on key metrics, we can expect some of these values on average. Now we have designed our model, we understood the hardware, we have the model ready. What is the next step? Can we do something more to optimize our model and reduce the size? Yes, the technique is called knowledge distillation. So we have this bigger model, but this model is still over parameterized because there is some scope of optimizing it further. Now, model distillation is a technique in very general sense where you have, say, a bigger teacher model and you want to train your student. So in a class, you have a teacher who knows about the concepts. He or she wants to train those concepts to the students. So this is basically if somebody is teaching a course, they are distilling the knowledge that they have gained over the years into the students in that certain amount of time during a semester, right? So it's something similar to that. The teacher is a bigger model that's over-parameterized, that has been trained. You can make a smaller version of the model that becomes the student model. Now, what happens in knowledge distillation is that the teacher model is already trained on a certain task. Now you freeze that model for knowledge distillation and you only train the student model. You pass in the same data through both the teacher and the student model. The teacher model gives you the output logits and the student model also gives you the output logits, which is the prediction. Now, what you're trying to do is basically the teacher model has some sort of a weight distribution. You are trying to bring the weight distribution of the student model as close as possible to the student model, to the teacher model. And the best loss for doing that is KL divergence loss. So basically, you apply the KL divergence loss and you only backpropagate through the student model so that only the student model weights are being updated. The teacher model weights are always frozen. So that way, you can actually distill the knowledge of the weights that the teacher has learned into the student model. One of the most prominent examples in transformers is DistillBERT, which was a distilled version from the bigger BERT model that you can use for a faster inference for text tasks. And these are some of the key metrics that you can get on these tasks. In general sense, in production, what I have seen personally when I use knowledge distillation, if I'm training a model from scratch, the student model from scratch, usually using knowledge distillation gives me 1 to 5% additional benefits in terms of performance or accuracy as compared to training the model from scratch. So this is like a really good technique which can be easily used. Now we have a model ready. Our model is smaller. We optimize it for the hardware. We have all the steps in. What's next? Model is still over parameterized. We can still prune the model. There is still a smaller model hiding somewhere in there. So model pruning is another task that we can perform after this. In model pruning, you can prune it either based upon, say, if you have convolutions, you can prune a single channel or multiple channels. You can prune the entire filters. You can prune specific weights. So based upon that, you will end up with a smaller model, which has been pruned. In terms of transformers, you have to be a little bit more cautious in pruning as compared to general DNNs or CNNs, because you can prune in two places. One is the self-attention layer, and second is the feed-forward network. Self-attention, as you know, in transformers, gives you, say, output probabilities. And even if the probability is too low, even then it's of utmost importance to figure out what's the next token in a text task. So that means you don't want to just prune it naively, because you might lose those very small values if you are doing, say, for example, magnitude pruning, where you prune only the lowest values. You don't want to do that. So you need to be really careful there. And similar thing applies to the feed-forward network in the transformer layer. So now our model, we started from a bigger model, we distilled it. Our model runs fine on the hardware. We have the latency, memory bandwidth, everything done. Pruning is done. My model is small. What are the caveats? I can do magnitude pruning. I can do structured versus unstructured pruning. I can either prune equally the channels across all the layers. I can prune them separately, like they might not be equal. I can also do local versus global pruning, like prune a certain number of weights in a certain layer, or I can do it globally. In terms of key metrics, we can expect some of these values up to 90x smaller models while maintaining performance. So what's the caveat here? It all sounds so good, right? It depends upon what your hardware supports. So if now with pruning, what we are saying is I have a certain kind of a DNN where I have chopped out some connections, or maybe I have set those weights to 0. That means given an input, it will be multiplied by zeros. The output will be zeros. My activation is 0, so I am not getting anything. So basically what that means is that it's not part of my network for an inference point of view. Now, if my hardware is not smart enough to take care of those smart matrices or those prune matrices or sparse matrices, what will happen is during inference, I am still multiplying zeros. So it's unnecessary compute that I am still doing. Although it might not consume too much memory, but I'm still doing the compute, which is of no use. Now, what you want to understand here is that if your hardware actually supports pruning and it can do sparse matrix multiplications, what in general sense happens is you can take an example of like A100 GPUs of NVIDIA. What happens in those GPUs is like, if you have a sparse matrix where most of the values in your matrix are zeros, at runtime, basically, it can bring all the non-zero values together in a matrix, do just the computation on that, and then provide you the final matrix out of that. So how that helps is that you are not doing additional compute. You're saving on the memory because you're not considering the zeros. And similarly, on the inference side, the new hardwares are smart enough that they can automatically do these kind of things. So you only want to do the pruning if your hardware supports it. Otherwise, it won't bring you the benefits that you want in terms of model size and latency and other kind of things. My model is small enough, but it's still at FP32, floating point 32 or floating point 16, depending upon if I train in full precision or mixed precision. What else can I do? I can do model quantization. So quantization in very basic sense is I have a model at floating point 32 or floating point 16, but it's still a huge range. My model weights are high. How does that matter? It consumes my memory bandwidth. I don't have that memory. What do? Reduce the memory bandwidth. How much can I do it? Whatever the hardware supports and whatever my framework supports. If my hardware supports only int8, I can only go to int8. So basically what happens is from FP32 in that range, I can go down to a range of int8, say between 0 to 256 or 127 to 127, minus 127 to 128, something like that. But what happens here? You end up with quantization errors. Why? I am taking values that are distributed across a very wide range, and I'm trying to bring them down into a very small range. So what that means, if two values are kind of close enough in a wide range, they will map to the same value in a low range. So when I'm trying to get back from the low range to the high range, I will have additional errors, which is my quantization error. But in general sense, how quantization helps is that if you see on the image on the right, if I'm doing a 8-bit addition, so our hardware does basic operation at a very basic level is multiply and accumulate, and it's doing multiplication and additions. So input, multiply the weights, do the additions, get the sum, apply activations, right? The 8-bit addition will consume this much amount of energy, which basically reduces your amount of power profile. And you can maybe increase the size of the SoC. Maybe you can add more amount of memory or processing elements. And you can make your product cheaper as well. But if I run it at 32-bit, then that means my model weights, first of all, won't fit on the device. I will have to go off the device to some flash memory and bring the weights in. So that adds to my memory bandwidth, that adds to my latency, that adds to my additional power, because every time I'm going off the chip to bring the weights in or activations in, I'm adding to my memory and latency. So that's consuming my additional power. Similarly, on the area cost, if my area can be reduced, if I say my hardware will only support 8-bit activation, 8-bit weights and activations, what that means is I can reduce my memory area. And as a reason of that, I can increase my processing elements. So if I increase my processing elements and my model is small because of 8-bit activations and weights, I can maybe process multiple models, or I can have better parallelization across all the processing elements. I can increase my throughput. So if you remember earlier, we discussed about the roofline model where we mentioned about the throughput and the latency and the memory bandwidth. So memory bound versus compute bound. So if you have more processing elements, you can be more on the compute bound side. That's where we love to be. In terms of quantization, in general sense, you can do it in two ways. Either you can do post-training quantization, your model is trained. After that, you can provide a calibration dataset, which for each layer will calculate the minimum and the maximum values in which you want to quantize. And then it will automatically quantize your models into like int8 or int4 or whatever you want. Or you can do quantization aware training, where during training time, you tell the model weights that, hey, I want during inference time for you to be at int8. So train it like that. So it will add fake quantization and dequantization stubs, and it will keep the weights during the forward pass at int 8 or int 4. But during back propagation, you still want to keep them at floating point 32. Otherwise, you will run into scaling issues because your gradients might become 0. Another way of how quantization is applied to transformers is low rank adapters or quantized low rank adapters, where you can freeze most of the model and just set the model weights to int 4 and the activations to 8-bit or 16-bit. Reason being, why can we not set the activations to 4-bit as well as we can do in convolution to 8-bit or 4-bit? Is because in activations that we see, the self-attention layer, for example, in transformers, their values can go all the way from very high values to very low values. So that means the activations actually have outliers. And when you map the outliers, you end up with higher quantization errors, which propagate even more in transformers. So due to that, you want to avoid keeping the activations to a very low bit width. You want to keep it at 8 or 16-bit, but the weights are still fine. You can still keep them at int 4. So that's what you see nowadays when you look at transformers that are running on device. This is what's going on behind the scenes. So in overall sense, these are the key metrics that you can achieve. We have quantizer model, we have pruned model, we have a very small model. So let's look at a quick summary. Neural architecture search, you can automate your model development, you can optimize the model, you can have a very efficient model, which is with the hardware in the loop that runs perfectly on hardware. Then we have hardware-aware design. You know which layers are supported, or maybe there are certain layers that your model can hardware can accelerate better. So you use that as part of your model development cycle, and it can adapt easily for your hardware. Then once you have designed the model, you do perform knowledge distillation. You want the model to be smaller because it's still over parameterized. So you can make it smaller, transfer the knowledge, keeps it still efficient, maybe have 1 to 2% or 5% more performance than training it from scratch. Then my model is still over parameterized. Prune the model if the hardware supports it, make it even smaller or make it run faster, less amount of memory bandwidth, lower latency. Finally, it's still in FP32, quantize it to int 8 or lower if your hardware supports it, and you have even a smaller model which is ready to run. Now, looking at a case study, we'll look at two case studies here. One is how we went from looking at a video which is 180-degree field of view from a camera like this, or a Panacast 50 or a Panacast 50 VBS. And what are the challenges of developing a simple model as simple as an object detector or a gaze estimation or things like that? Now, when we talk about object detection, it seems like a very general, like a simple problem. It's already a solved problem, right? So what could go wrong? Interesting. Well, try putting an object detection model in production where people do all sorts of things. There are all sorts of like plants and different kind of animals and things walking around in terms of false positives. And you'll be amazed what kind of things it can detect as a person actually. Another problem that comes in is that you have this 180-degree field of view. That's almost like a 32:9 aspect ratio. You are passing this higher resolution input, maybe at say 1080p, into your model. So as we saw earlier, the bigger your input, the bigger your activation, even though your model weights are fixed. So these become like a big issue. Another thing is I want to detect people who are in small to medium rooms. That means I could be detecting people who are maybe say 1 to 20 people in a room, sitting at anywhere between say 5 to 8 feet to all the way to 20 feet. As people go farther away, they become smaller in size in terms of pixels. So it becomes a really hard problem to differentiate between the false positive and a false negative to detect a person. So like Narsi mentioned in the previous presentation, let's look at what are the requirements that we were looking at, and then what were the options that we had and how we went about deploying the models. So in terms of Intel Myriad X, since this model is deployed across two devices right now, Intel Myriad X and a Qualcomm processor. So we'll talk about both of them briefly, how the life cycle looks like in terms of development. Rest of the techniques are kind of common, but wherever some amount of optimization apply, I'll talk about them for Qualcomm. In Myriad X, you know, entire system is like 3 cameras for this big sensor going in, 8 microphones going in. Audio has a separate path. Video is there. Both are sharing memory. In this SoC, we have this small part. And even in this small part, we have this small dot. That is what is available to me to run this model. Like Narsi mentioned, he only got out of 6 shaven slices, maybe 1 shaven slice. I'm lucky I got 2. So the compute is limited, memory is limited, latency again is limited, because instead of a single camera in that case, you're now streaming 3 cameras which are getting staged, and pre and post processing and all those things are happening. Bigger frame resolution, more amount of memory. So latency is the issue. It needs to detect people as far as like 20 feet. Even in this room, it should be able to detect it. People can deploy the camera anywhere, irrespective of whatever you specify it for. Precision needs to be good. So people don't care. They are buying a costly product. The precision needs to be really good. The trade-off again is accuracy versus latency, and accuracy versus memory bandwidth, and the number of detected people, as we talked about. If we look at Qualcomm architecture from a very high level view, because every architecture has some specifics, you are looking at a CPU which is a bit more powerful as compared to Miridex. Miridex is just kind of like a CPU with like a couple of threads with couple of acceleration parts. You have a separate dedicated GPU that can support floating point 16 operations. And then you have a DSP, and there are a couple of other options in the DSP. One could be for application-based, one could be for compute-based, but here we are just talking about the compute-based that is specifically for image processing and computational photography. So it's meant to accelerate convolutions and other kind of operations well. So in this also, you have 2 kind of different things that might be available across products, which could be an HVX and HTA processor. The HVX is basically a compute DSP, hardware vector extensions. So this supports int8 quantized models that you can run. But again, the kind of layers that are supported may or may not be limited depending upon when you're developing the models. Because like, for example, I was developing a model and trying to deploy it on that, and Silu activation layer were not available on this or not supported. So I had 2 choices. Either I decompose that Silu activation into some simpler operations, or I fall back to a ReLU activation that adds sparsity and it's easily available across the board. But then I lose performance by around 5%. Then you have a AIP, which is the hardware tensor accelerator, which is like a very, very specific matrix accelerator with 2 specific threads that provide hardware compression. And that actually has a subset of layers that CDSP supports. So that means you are going even lower, but now you have int8 and floating point 16 support. It can run a little bit faster if you can put all the model layers on this. Now here's the caveat. If I am not able to run all my model layers either on AIP or on CDSP, those layers will fall back on the CPU or on the GPU. Now for each of the fallback layers, there will be additional read and write operation. So added memory, added latency, right? So that becomes an issue. Precision will change. CPU does not support int8 maybe. So what do? Floating point 32, precision changes, my model accuracy is gone. Additional amount of memory jumps will have to be done. So those are like some of the issues. Now, once the model has done processing, you apply an ONNX separation or whatever, you get your outputs, bounding boxes, classes, pass that back to the GPU or the CPU for rendering if you want. So in general sense, if you have a video input, you get a video output with bounding boxes. Something like this will, it'll look something like this. In terms of workflow for Miridex, Narsi mentioned about how to go from like PyTorch or ONNX to deploying them. And Fabricio will be talking about that a bit more. But here, in very general sense, these are like some of the things that it supports. So you basically have your model trained in PyTorch, TensorFlow, Keras, or whatever. You convert that into either ONNX or Snappy framework. If you are using it, directly supports all the models. Like if you are using PyTorch, you will have to export it to Torch script and things like that. Once you have that, you pass them through the frameworks, you get a specific binary. Snappy gives you like a DLC file. So what this compiler is doing, basically, it knows that what layers are supported. You will define a runtime where you want to run it, CDSP, AIP, whatever. You define that. Based upon that, it will select a couple of layers. It will make the optimization again, kernel fusion and other kind of optimizations, replace the layers with some other things. If it has to do some kind of graph optimizations, do like int8 optimizations using some kind of built-in quantizations if you haven't done it already. If you don't provide a quantized model, it will do the quantization for you using ADA round and other things. And then basically, finally, you end up with a binary file that you can deploy on the specific hardware that you defined for the execution. So memory bandwidth, we already talked about earlier, what it looks like. For each of the layers, you have intermediate activations. The model weights are constant. Inputs and outputs So all of this comprises of the memory bandwidth. That's the first challenge across both the devices. Memory is the issue. Model latency is another issue. Like Narsi mentioned about the skip connections. If I want to have any kind of skip connections to pass the features forward, it gives you good advantage in terms of additional regularization and things like that. But then you have issues while running that on inference. Of course, you don't want higher latency. You have a latency budget across both the devices, whether it's int8 or FP16. You have a little bit of more flexibility on the int8 side, but then accuracy also kind of decreases if you are not cautious there while converting your model from FP30 to int8. So the best way there is to train it as close as possible to your inference runtime. For Miridex, for example, floating point 16 is only available. We try to train our models with mixed precision or half precision, so that when we are exporting the model, there is no to very minimal loss in accuracy, and that's what we have seen in production. Similarly, for Qualcomm hardware, int8 is supported. Train in half precision, then deploy to int8 or use quantization aware training, so that when you deploy a model, when you do the conversion for the model, your model still runs to approximately the same accuracy that you see in the bigger model that you have trained. Another challenge, model accuracy. So synthetic data set that Narsi was talking about, this is something that it looks like for the Panagas 50. You can see like people could be far enough. People could be doing like different kind of gestures. In terms of input resolution, it looks kind of like this 180-degree field of view as compared to the smaller one that will offer. So the bigger input resolution, you have to look across the entire image. You have to detect the people, do segmentation, pose estimation, whatever. So all the problems apply. Dataset limitation, of course, everyone has heard about that and everyone has it because dataset collection and annotation is the costliest process. So just to give you a basic sense of what the challenges look like, this is what it says. So in a meeting room or while standing or wherever the camera is deployed, healthcare setting, meeting room setting, any other setting, people could be facing sideways. People could have long hair where you don't even see the face. If the model has learned to extract just the facial features, how do you detect them? So you need some kind of temporal consistency or variation in the data set there. People could be facing away from the camera where you don't even see the face. You only see back of the head. And if the person is sitting with the black jacket and the black long hair, the model might think it's just a black blob and it will say it's not a person. It has happened to us actually in production and in testing in office. Person is far away from the camera. Person is too far away. The pixels are too small. We want to avoid false positives as much as possible. So a better way is to not detect the person or to use temporal consistency to keep the person there when they're moving farther than to have a false positive there. Because in the end experience, the false positive hurts more than not detecting or using temporal consistency for us. Another, people might be partially occluded. What if you are making a decision for framing a person and you don't even see the head? And if you're using just the head for framing decisions, that person is basically invisible to you. So what's the problem impact? These are the actual impacts that we have seen in production. When I joined for this smaller device, we had an issue where the model was having some kind of false positive. We sent it to Microsoft for certification. They said there are false positives, you need to fix this. I spent my entire weekend and the next week just collecting more data from different sources, from commercial sources, as well as generating synthetic data, going through all the annotations, making sure annotations are clean, training and fine-tuning and iterating through the models, making sure the accuracy is good and it does not have the same false positives. There is a reduction in that because we have a holdout test set for all of those things. At the same time, making sure I'm not changing the architecture too much or the latency or any other thing. So I need to take so many things into consideration before I can make a decision that, okay, the model is ready to go out. That's just certification. It's not even going out to production to people. This is just initial internal testing. Similar thing happened on Panagas 50 and Panagas 50 VPS. We were using an older model before. What happens? You pass in this big input. Now, depending upon if the model is big or not, if you have more number of people, that means you are having more number of outputs and there is some additional load there. You run out of memory at some point of time. If you run out of memory and the camera is running, you basically run into frame corruptions. Your frame starts corrupting. You see like blobs coming up in the frames. You're like, what's happening to the video? It's a really costly camera. Or otherwise, the camera might just crash. That's the worst case scenario. So in both the cases, we don't want that, but that actually happened. So for all of these things, that's why we reiterate memory bandwidth, latency, performance, all of them are equally important. We cannot just have one and the other. So the goals are input size is fixed. As Narsi mentioned, for Mediatex, floating point 16 is fixed in the hardware, can't do anything about that. Model parameter reduction is something I can do, but again, sparsity is not supported on Mediatex, so can't do pruning there. Precision should remain the same, less amount of false positive and false negatives. So again, trade-off between memory bandwidth and latency. So a lot of things. In terms of model designing, as I mentioned before, half precision training, so that as I go to FP16 model deployment on Mediatex, I don't have loss in precision. And similarly, quantization aware training for Qualcomm hardware, so that I don't lose precision when I go to int 8. In terms of convolution, use efficient convolution layers like we discussed before. Ghost convolutions and partial convolutions, depth-wise convolutions actually add a lot of memory bandwidth. The reason being, for each of you are taking each of the separate channels and in doing convolution with that. So you have to read and write a lot of those and keep them in memory separately as compared to a normal convolution. So that did not help a lot. Feature size, as Narsi mentioned, we have this big of a frame, which is even bigger than what the Panagas 20 actually has. So the biggest thing is take all of that, make it small as soon as possible by using a bigger kernel size or using like space to depth kind of layer, so that all the spatial dimensions go into the depth without losing the features. You at least make the input resolution as small as possible. How does that help? You can process it faster. Your activation size will be smaller as you go above, and your memory bandwidth and latency are in control. Space to depth, pixel shuffling, architecture, make sure everything runs on NCE, and same for Qualcomm, all the layers are supported, and we don't have to hopefully write any custom ops. So just some solution in detail, as I mentioned, space to depth. I have this big image, which has RGB channels, so pushing them across depth so that my spatial resolution goes down into the depth without losing the features. In terms of the performance metrics, what kind of things do I get? If I use a convolution 2D with a batch num and a ReLU, I get something around 352 bytes in parameters. For space to depth, I get only 150. It's almost half. So this actually helps me a lot when I'm doing that in the feature size, because this is saving me both in terms of compute and latency and the memory bandwidth. Similarly, like Nasi mentioned, using DenseNet kind of layers or the architecture, where instead of adding all the features at the end, you are concatenating them, as well as you are calculating all the features and you are reusing the features. So when you are calculating a feature for each layer, a different feature, and then you're reusing that and concatenating at the end, that means you are reducing your memory bandwidth, because you don't want to recompute all the things. Whatever you have computed, you are reusing at the end and concatenating them. So you have all the same features while the in-between features. So that way you are reducing your memory bandwidth for additional feature extraction there while maintaining the performance. So what do we get here? You have a dense feature block where in comparison to a convolution batch num ReLU, you have 18.56K parameter, whereas you can reduce that to 15.53K parameters. Ghost convolution, as we talked earlier, convolutions have a lot of feature repetitions. So as you can see in the image, the red ones are basically kind of look similar. The green one looks similar. The blue one look kind of similar. So you can basically reduce most of them and reduce computation and the memory bandwidth. So use some kind of ghost convolution where you reduce the number of output channels for the first convolution, and then use cheaper operations to calculate rest of the features, using maybe depth-wise or partial convolution and things like that, where you can save on compute and memory. And what do we get out of this? Again, good amount of reduction in terms of max and number of parameters across the board for the same number of input and output channels. We talked about partial convolutions as well. We get some kind of optimization here. We are, just to remind you, we are just copy pasting half of the channels based upon a metric where we are just masking out rest of the channels which are not useful features, or we don't want to recompute them, which are repetitive. We just perform convolution on a certain set of layers and don't do it on the rest of the features. We just copy paste them to the next layer. And in this, we have a good amount of parameter reduction. So for normal convolution, for 9.28K parameters, we go down to 742 bytes. That's a good amount of reduction in terms of both compute, memory bandwidth, and the latency. One caveat here in partial convolutions, this number is there when you have same input and output because you are concatenating the channels. So that means you cannot change the output dimension. It will not work there. So if you want to concatenate them, that's where you will come closer to the convolution number of parameters and MAC operations, because you'll have to add additional maybe one by one convolutions there for adding increasing the number of channels for the layers that you copied. Then replacing transpose convolution that we talked about, again, using pixel shuffle or unshuffle, which is basically kind of a no-op. You don't do any operations. You are taking just everything from the depth and pushing that into the spatial dimension. And you are getting the output in terms of, instead of doing transpose convolution for upsampling or downsampling, so you are saving compute there. And what we see in the numbers, the execution time is less overall on the Mediatek hardware. So in terms of milliseconds, you are at only 0.228 milliseconds as compared to 2.98 milliseconds. So as Narsi showed that for the model itself, we only had like 18 milliseconds and end-to-end pipeline 33 milliseconds. So every millisecond counts. So what was the impact of the choices in terms of the object detection itself? Overall, in terms of the latency, we achieved around 20%, 30%, 40%, 15% reduction across the board using these choices. In terms of the memory bandwidth, we had these kind of improvements across the board. And finally, the models are all deployed. They're all in production. And yes, there are always a little bit complaints here and there about long tail problem, because there is always an edge case, and everyone knows about the long tail where you can fix most of the things through dataset for most of the part in a distribution. But you always have a long tail where there might be some edge cases that you always have to solve for. So that's where you need to add data and reiterate a little bit. But overall, we're pretty happy with the performance. So here's two videos, one of object detector running on that camera, and another one running on our Panagas 50 and Panagas 50 VBS. So here you can see the bounding box looks kind of pretty stable, and that's because we also added temporal stability to this. In terms of temporal stability, we tried two approaches. So the architecture basically looks something like a YOLO architecture, where we are utilizing all of these layers combined. In terms of temporal consistency, we tried it two ways. We added a conGRU layer at the backbone before passing it to the head, where you do upsampling for individual scales. And we have three scales at the output: small, medium, and large. We tried another approach where we tried using LSTM layers, but that was like individual LSTM layers for each of the scales, like for each of the heads that we have as the output, and try to add there. So what we notice is that that adds too much amount of latency and compute. So adding them just at the backbone works equally fine for us. It reduces the performance by a little bit, but given the trade-off, it's still good enough. So here you can see the person moves their head up or down, goes close by, is far away, and it's totally fine. We don't see any issues. All the results are above 90% in terms of performance. Temporal stability is good. So we don't miss a frame. If you just train on images, you see the flickering issues sometimes. In temporality, you see much more smoothness kind of. Similarly, we have Panagas 50 and Panagas 50 VBS with 180-degree field of view. So this is what a room would look like in a 180-degree field of view. And we need to detect every person from each end to each end and everyone in between. We cannot miss anyone, irrespective of partial occlusions or any kind of artifacts or any things that they are wearing, maybe like headphones or other kind of thing that might look like a person. And based on this feature, we have made a model that's good enough, but now it became a little bit too good because as after COVID, offices started opening, the IT guys thought it's a good idea to have more open spaces. So they started adding glass walls, transparent glass walls to the meeting rooms. Now the model, if you deploy the same detector in a small, medium meeting room scenario, it works well. But if somebody is walking from outside, it will still detect them and it will frame them as well. If it's a, say, intelligent zoom feature where it's zooming onto the people or just framing them separately. So given this problem, we had to figure out a solution, and we came up with a solution using, the thing is, we don't have additional compute on Miridex. We don't have additional memory. We cannot put additional model. We cannot use a depth model. We cannot add anything extra that could help us. So what do? We came up with a clever trick using an algorithm that's patent pending, but we'll tell you about how the thing looks like. So on the video on the left, what you see is people sitting in a room, and you can see people sitting outside. So the intelligent zoom is framing the people sitting outside as well, because it's able to detect those people as well, right? So you see the experience is not that great because the camera is moving around. It's more distracting. At the bottom, what you see is using the intelligent meeting spaces that you can define. It could be either a room or it could just be this place where you can just define your virtual meeting space. The camera knows, okay, these are my limits. It will not detect people outside, but it will not frame them. So it knows whoever are there. It knows where the people are, but it won't frame them. So that's the intelligence part of it. Okay, awesome. Enough of me. Any questions so far? Otherwise, I'll give it next to Fabricio. Yes, sir.
My question is more around the observability of so many different parameters. And, I did like tweak one thing, the other. How do I know what inspection? A lot of like statistics and a lot of cool sites into your model. So what is I guess the tooling or the way you actually get the observability of the
Yes.
easily? So is there any like recommendation around that or any recipe?
So there is no recipe that fits everyone. That's what I'm saying since the beginning. It's a software hardware co-design problem. First thing starts from understanding the hardware, because writing the model is the easiest part. You can train the model, write the model. Dataset collection, annotation is the hard part. Understanding the hardware is the hard part. Because in most of the companies, either that process will be separated across teams, and then there is a gap between the communication gap, and that's where issues happen. So for me, I was lucky enough because I was working across both the things by myself. So first step, I would say that understand the hardware and what tooling does your, like if you don't make the hardware, whoever is the vendor, what are they providing? Go through documentation. Documentation provides you a good amount of things. Go through some of the examples, go through some of the SDKs, how they implement the kernels. Do you have the flexibility of implementing kernels? If you have, maybe you might be good with the binarized neural network as well. So you need to understand that first. Once you understand that, you have some idea around the search space that you have. From there, it's an iterative process, which is comparatively easier because you can just do like a grid search or as like a naive search, or you can do neural architecture search and things like that for the model part. And that's the easy part. Understanding what things are available to you, what are the limitation or the bounds that you have to work for within. For example, what's your bit width maximum? What's the minimum maximum bit width? Does it support mixed precision? Does it support intent? What does it support? What kind of layers does it support? Am I using those layers or not? What kind of performance difference do I see if I use this layer versus that layer? What kind of frameworks does it support? Some of them might not even support all the frameworks. So you might like, even that will decide what framework you support. It's not the other way around. Like you write your framework and after that you will have to deal with a ton of things where you go through model optimization and conversion just to bring it closer to deployment on the hardware. And there in between something might happen and you might lose some performance. So there are like a lot of things, and it's an iterative process that you have to go through by understanding the hardware and then going through the software and having a core design there. Let's move on. Yes. Yes. So we do keep it to original aspect ratio because if we change the aspect ratio, what we have seen that it might distort the people or what the models are learning. And that causes a lot of issues because we want to keep our training data set and the training thing as close as possible to the test time. So whatever the model is seeing is the entire video that then downscales and runs through the model. So we try to keep the aspect ratio to the same, but we have tried different kind of like augmentations around that, like using mix up and other kind of augmentation that we have tried to see if that works or not. But we had tried with the aspect ratios, but it didn't give us too many like good results. We also tried like training with a very small size and then going up from there. We did see some amount of improvements, but maintaining the aspect ratio actually helped a lot.
Okay. In fact,
I can take it later.
Yes, we will stay here even after 5:30 to answer all the questions. Okay, then let's move on because we have a lot of presentation yet. Elizabeth and Sean. In my case, I'm going to change a bit of perspective here, and I will try to show you in practice how to deploy models into the MediaDex device. In my case, what I'm going to show to you, it is in terms of gaze correction, okay? The idea here, it is that we keep the eye contact from a model, and this model is going to be executed into the OpenVINO media decks. I'm going to show you the steps, but basically what I want it is once I have the trained model, the idea is that I convert this for ONNX and they have the last part of in terms of optimization. Then you can deploy directly into the camera. Then basically the pipeline it is. I'm going to have here just a moment. I need this resource now. Yes. The model development is the one that you usually work in the day by day, okay? Developing a model, a neural network using PyTorch, using TensorFlow, then this is the one that probably you have performed at least once in your life. The idea it is, once you have the model, we're going to convert this for one ONNX version, and ONNX is ideal because it's a universal format. If you have the ONNX, at least the expectation to convert for ONNX, it's quite easy to convert to the blob. And the blob is the format that we are going to deploy into the camera. And OpenVINO, it basically, sometimes we call this is OpenVINO, another time MediaDex is the same chipset, but Intel provides to us the compiler tool that helps us to convert from ONNX to the blob. Okay, once you have the blob converted and it's VPU-based blob, we can apply one inference and deploy the module into the camera. I'm going to give you more details about the module later, but this is the architecture, the basic architecture from my Jabra eye correction, okay? And we have a mix here in terms of knowledge. Then let's say these blue rectangles are the neural network split in 3 parts. And these are the one that I'm going to focus today in terms of how to deploy into the camera. But I also have some steps that involves engineer and computer vision. Okay, but the idea is that I convert this entire pipeline and can execute into the camera. Okay, but I'm going to consider like only the color model for the moment. Once I have the model trained, the first step it is converted to ONNX. Then the one that I use more in the company, it is the PyTorch. Sometimes we must implement it also in TensorFlow, but I'm going to focus in PyTorch. And the library itself provides to you different methods. You can use the export, okay? And the export, it was replaced by this Torque Dynamo. And how it works my pipeline. I have everything implemented using DVC. Then it's only executed the DVC every time that I increase, for example, the database, then I started training the entire process. My DVC, it has the entire pipeline that it's gonna download the data set, pre-process, apply the data cleaning the data set, it started the training process. Once it's achieved the maximum number of epochs or a better accuracy, I'm going to evaluate the model. And in the end, I will deploy the model, convert this to ONNX. Okay, once I have the ONNX, convert to the blob, and this is the entire automatic process. Then I can deploy into our experience zone. Okay, then everything we implemented this step automatically, and it's going to be executed only using the DVC. But in terms of code, you are going to see that's quite simple. Okay, then the code that I'm going to show to you, it's a simple Python code. And as you can see, sometimes 2 or 3 lines of code. To install, like the ONNX, to export or to apply the inference, it's only basically 2 pip install. Then these are the libraries it's needed in your Python environment. In my case, I use the Conda. Then once I install this, very short process, I can start like deploy the model. In my pipeline, after training the model, I have the checkpoints ready. I can like create the module itself as one object. And this is only to define, okay, this is the format of my tensor, the input tensor I'm going to feed the model. It could be any random data, because the most important here for me, it is the shape. Once I have this, I can only include this line of code, and it's a simple line of code that is going to evaluate the model and convert this to ONNX. Once you have the ONNX object in your hands, it's only apply one save and define what is the path you'd like to save your ONNX. And the best here, it's going to be universal, as I said to you before. Then I can start like deploy for different platforms. Even in Python, as you can see, 3 lines of code, it's only import ONNX, and this is the runtime. I can load again the same ONNX and start using the ONNX as a module. Okay, as you can see, it's quite trivial, the steps in terms of Python development. Probably you know, but we have this Nitro application, and Nitro applications can help you to see, okay, how is the overview of my model? You can go into this node and see what are the weights, and they have basically one overview about the model. And in my case here, this is the same architecture from that color model I said to you before. And what I've made here, as you can see in parallel, I execute the same model twice. Why? Because I have the left and the right eye, okay? The only thing that happened with me here, it is I needed to include this part because to convert to ONNX, it works quite well to have like 2 inputs and 2 outputs. I can feed my model with the left and right eye image, and have the output with the transformed image as the left and right output. The problem it is when I converted from ONNX to the blob, I lose this information. Then what was the idea? I keep the same weights in terms of my architecture from my model. I only included here this step. And what is that? I'm gonna, like before feeding the model, I'm merging, okay, in terms of channel, the left and right eye image. I feed this as only a single input. Inside the module, it's only split. And in parallel, I'm gonna execute the left and right eye image. At the end, you can see it's only one concatenation. I concatenate the result, and I have like basically a single input and a single output. This was the alternative that I found, the easiest one, and I'm not gonna change, and I don't need to retrain the model. It's only one small adjust I had here in my model. Is that clear, this part? Then I have the ONNX universal. What is the next step? It's the blob. And the blob conversion, I'm going to use OpenVINO toolkit, and OpenVINO toolkit is going to provide for you all the tools needed to apply one of the techniques explained by Anuj. Then I have the post-training quantization, okay? 2 steps only. The first one is the model optimizer, and this model optimizers get the ONNX that we had before and convert into files. One XML that basically describe the architecture of my neural network, and the second one, that is the bin. Okay, once I have this, it's only feed again these 2 files, and I can generate like the blob. And this is the one that we try to achieve, and I need to specify, okay, this blob, what is the type of the blob? It could be VPU, and the VPU is for the MediaDex executing here. This is the important one, but it could be also CPU, it could be GPU. Okay, you can convert in different formats. But the one that I'm going to try here, it's convert this into the MediaDex. This is only the diagram, as I said to you. It's the ONNX, then I apply first the optimization, and after the module compiler. Okay, the blob is the one that we are going to install directly into the camera, okay, deploying into the camera. In that case, I'm going to use this camera that I brought today. It's the Luxonis. I'm not sure if you know, but it is OAK. It means Open CV AI Kit. Okay, then this is another name for this camera. Thank you. Okay, in terms of the optimizer, it's everything that you saw before that Narcy and Anuj presented for you. The first one, it's in terms of the type of data that we have, we are going to execute in the MediaDex. Then the format here, it's going to be FP16, okay? When you deploy this, when you convert this into a blob, it's not 32 anymore. It's going to be converted for FP16. We also have a normalization, because the same way that you work with OpenCV, OpenCV provides for you one image as one NumPy array, and the range of these images from 0 to 255. In most of the models, you need to normalize between 0 and 1, sometimes -1 and 1, minus 0.5 plus 0.5, doesn't matter. But you have this normalization step. You can include the normalization step directly when you convert the blob. Then you can feed like the NumPy array that represent your image, the same format as the one used by OpenCV. And the model itself has the first layer to apply the normalization. Okay, then you can decide if you wanna feed as unsigned 8 or even FP 16. Okay, this is something that you decide. Another point it is you must take care, I guess, if you had this experience before to work with both PyTorch and TensorFlow, you know that sometimes the channel came in first, the channel came in the last part. Then you need to see how is the format. If channel, it came first or in the last one. And another problem for us that work with OpenCV, sometimes you see that we execute in BGR, but it could be the model training in RGB. Then it's something that we must take care as well when we apply the optimization in practice. As you can see, one line of code, once you have the pip installed and you have access to the ONNX, how to convert the ONNX into the bin and the XML file, the first step in terms of optimization. Then the post-training quantization, it's this line of code here. You can open the terminal and execute in a couple of milliseconds. You have the first two files, and it is optimized to be executed here in the MediaDex. Okay, of course, you can apply before all the techniques explained by Anuj, like pruning, but in this case, I'm only apply the simplest optimization, and it's only a single line of code. Okay, then it's gonna save the bin for me and also the XML. What I need now, it's basically use the compiler tool. And the compiler tool, it is the one where you are going to define, okay, what I want as input layer. I want with or without normalization. Then you can have this flag here. And this flag basically tell to me, okay, I'm gonna use unsigned 8, okay, to power 8, I have 256 representation. These are the grayscale levels that represent my image. Then I can provide this information. Or if you are going to normalize by yourself, okay, with the range defined during the training module, you can also specify that this is without normalization. What you have considered it is the chipset provided by Intel, this MediaDex, it has like 16 shapes, okay? For default, when you compile from the bin or the XML file into the blob, usually be that you are going to execute in 2 shapes or 2 threads, okay? But you can go up to 16 shapes. Because in our case, as I said to you, the engineer team from Jabra sometimes give it to us only 1 shape, but we need to adapt it for the requirements to the process. Okay, but in general, the maximum number of shapes you have is this. And as Anuj mentioned for you, it's not possible to increase it, like number of shapes, the thread, or the memory available in the hardware. Okay, we always need to work over this limitation. Nice. To compile nowadays, it's quite easy because you have 3 alternatives. The first one, it's using the blob convert, that is a library available on Python, okay? And basically, it's gonna, in practice, use the second one, that it's the website called blob convert, okay? I'm gonna get the ONNX, send it to a server. It's gonna be like converted to a blob and return for you the result. The third alternative that I have here is to use the local compilation, okay? We have, in that case, some security aspects here to consider. If you use the first 2 options here, what's gonna happen? You are going to send the model for some server and you don't know where is the server. And maybe you don't wanna execute this. Most of the case, and it's the case that we work at Jabra, we apply the local compilation. Another problem that I'm gonna face, at least I face it in the day by day, it is, this is my company's machine, and this is MacBook use M1 processor. Use the M1 processor to deploy develop or to work with OpenVINO, it's really a headache. Okay, I really have a second machine. This is my personal machine, and it's still Intel based. Then when you work with the Intel based processor, you usually work very fine. But if you are going to the M1, probably you are going to face some problems. Okay, I would say that it takes a day that until you compile and have this machine ready to start deploying models. In terms of the first option, you will see that it is easy. Nowadays, you don't need, in fact, to compile it from the bin and XML to, after that, have the blob. You can get the ONNX directly, okay, define the type, define the number of shapes, and this code here, it's going to generate as output for you the blob directly, okay? Because internally in the website, it applies for you the optimization, then after that, the second step. Then you don't need to apply all the steps at the same time. The only thing that you need to remember it is this model is going to be sent for some server on the internet, right? Okay. Second one, it's use the website. The website, it's available in that link. All the slides, you can have access. I included like the link, then you can click on the QR code to access the website, or at least the links that it is related to the slide. But in that case, the website, it's quite simple. And what you can notice, it is the version that I have used here, it was 2022.1. We have now like 2024.1. And why it's not available here in the website? Because now it's deprecated, the VPU. Okay, you don't have the access to the media decks anymore, and Intel doesn't provide support anymore. Okay, in the newest OpenVINO toolkit, you can deploy for GPU, you can deploy for CPU normally, but if you want to execute in the media decks, and especially in the Luxon's camera, you must go up to the version 22.1. Then we have this limitation here. Okay. You can select the option, and you also have here, like if it is OpenVINO means the bin and the XML file, or if you wanna like deploy from the ONNX. This is only one option. And then what I'm gonna say to you here, I have included this part here, the XML, and the second one, the bin, okay? It's only specify what are the parameters I have. It's the same unsigned because I'd like the layer with normalization. Then it's only press. It's going to process in the server and send to you, download automatically for you, develop, then you can start using. As you can see, also quite a trivial, this step. And the last one, it is the alternative when you compile in your computer. If you try to find most of the documentation, it shows to you that you need to use the compiler tool, then it's a command in your terminal, but in fact, you have the Python code. And the Python code here only works because this device name is Mediat or MediaDex. It's only available up to the version, as I said to you before, 2022.1. If you try to compile with the newest one, you are going to get an error here because this option is not available anymore. Okay. Then let's think about the camera itself. Luxon is quite good camera in terms of prototyping, or at least applying practice computer vision for edge AI. I strongly advise you, if you have opportunity to work with one of the cameras, then we have different models. I bought two of these, it is the Luxonis OAK1 Max, because it has the same architecture as our camera from Jabra. I'm talking about the same architecture, okay? We don't have the same image quality. It's far away. I mean, the quality of the Jabra cameras, we have really better quality in terms of post-processing, in terms of image quality, in terms of even the quality of the lenses. Okay, but the architecture is normal, the same, but when I execute like the gaze correction, use the Luxon and use the Jabra camera, you can see that the eye image produced by the Jabra camera, it's really better. Okay, but let's talk about the architecture. at least it's one camera, you have a video streaming, and you can start processing some module directly to the camera. What you need to understand it is, in the camera, I must create a pipeline, and the pipeline is composed for different nodes, and each node you can find different inputs and outputs, and it's only a matter to connect. As you have in your hand now the block, the principal node you are going to use is the neural network node, okay? Because this is the node where you can load the block from your computer, and your computer is acting as a host, and it's gonna send the block into the camera, and this could be executed. And when I mention a pipeline, you need to imagine one diagram like this. This came from the official documentation. This part here, it depends on your application, okay? In my case, my gaze correction, I needed to create one pipeline similar to the diagram I showed to you before, and I'm gonna show you also at least 2 more times, okay? But I need to connect. This one is quite simple because it's only the camera. The camera is like OpenCV, always provide to you a video stream. You can collect frame by frame based on the frame rate, and it are going to send messages, okay? What is the message? It's basically the current frame that I just grabbed from the camera, and I can send it to the neural network. The neural network is gonna perform what? I don't know. It could be body detector, body segmentation, gaze correction, landmark detector. This is the technique that most of you produce in the day by day. The neural network provided also one output. Sometimes it could be one image, sometimes one numpy array, depends on the application. And you can get that one, let's say in this case, it's only one image, and I can show as one output. Then you need to understand, this is the idea here. I removed most of the source code because you can find the source code in the documentation. Then it's quite easy to understand and read because this is only Python code, okay? But in the perspective, let's say, the neural network, it could be one edge detector. In this case here, this node has like 2 inputs. One input that is provided by one image, and this is quite clear for you. You can connect with the output from the camera once the camera provides to you images. And you can also have some configuration, and this is the second input from your node. And in the end, you are going to have one output image with some modification provided by the neural network. Then what I've made, as I said to you, is the same architecture. I try to convert like this architecture from my neural network based on gaze correction into the pipeline for the camera. And basically, I reproduce like this architecture here with the pipeline. Okay? Then this is the part, the fourth part. I'm going to start the last one, where we're going to show you different modalities, different interaction modalities that we implemented in our camera as one experience zone inside the video tech team at Jabra. Don't worry, in the end, I'll open for the question, and you can ask us questions regarding to the development here. In terms of multimodality for Edge AI, in our team at Jabra, we try to think now about multimodality or interaction perception. And the meaning it is, we try to identify like the needs from the user, or monitor the user needs, and we can use like the eyes, gestures, voice, where the user can interact directly to our business product. Because as you can imagine, one situation, you saw that, especially the Stanacast camera, it is used in a meeting room, and sometimes only the host has connected like the computer into the camera, and the host is the one responsible to interact with the communication platform like Zoom or Teams. And my colleagues, how can, for example, can activate and mute the microphone, or enable, disable the camera, or at least practice with the most basically commands available in the platform. They need to ask me, but we can use like different alternatives that all the participants from the meeting room can interact with the camera and can interact with the environment. Only use different alternatives of interaction. And we try to bring like most of these technologies into our camera. In my case, I work with gaze correction. As I said to you in the beginning, I'm one eye tracking specialist. My master, my PhD was working with eye tracking. Most of the time to identify the gaze, the coordinates that the user is look at on the screen that we called as gaze estimation, or use the eyes to interact for disabled people that doesn't have movement for the arms and cannot control the computer with the alternatives device. But at Jabra, my mission, it was implement one gaze correction. Why? As you know, in the computer, when you are in a virtual meeting, we are going to lose the eye contact because the camera is not placed exactly in the center of the screen. Then if you remember, most of the time when you have one virtual meeting or hybrid meeting, most of the participant is looking down because the participant is not look directly into the camera, but around the screen. Then what we miss some engagement. And that's what I'd like to improve here, to have better engagement between the user, to increase the attention. Then I'd like to emerge the user more as a natural conversation in the day by day as you have a person in person, okay? Then the idea it is, this is a normal video, okay? Then I'm looking around the screen, and as you can see, I'm not so engaged in that meeting. What is the idea here? That I can identify the eye regions and the process on the eye region to reconstruct the eyes. What I have used here, NVIDIA Maxine. This is an amazing tool, okay? As you can see, it's the same video as before, but now I have more eye contact and sees that I'm really engaged with the person in the other side during the online meeting. I brought to you like frame by frame, and you can compare it. As you can see, if you compare like the background and even the head movement, it's exactly the same frame. Not I, in that case, Maxine, reconstruct like the eyes, all right? I have several problems here regarding to the Maxine. For example, it's not possible to execute my Mac. I needed to execute this in a GPU. And as you can imagine, it's a very heavy process. I cannot get the Maxine installed directly into the camera because the limitations from the camera. Then what I've mentioned here that, because this work I may execute even before the Maxine, but the focus, it was executing this module in real time, okay, because I had this challenge, real time to execute here directly into the camera. I need to think about how to optimize the module that it could be good enough to execute in our camera. I need to also think about diversity because I had several eye colors, eye shape, skin colors. Then I need to implement one model that it could be adapted for any person that using our camera. And at the end, it's looking for the integration, how to integrate this directly into the camera and the video conference platforms. I still have some problems because this is the original image. But what happens if I even apply one gaze correction? I can have one result like this. Okay, it could be strange. Even if you use most of the application nowadays, you will face problems like this. Okay, not only occlusion, even different light is condition. I can mention for you here most of the problems that you face in common video-based applications. What I tried then, it was looking for implement again or warp, and basically again can like regenerate the entire image from the eyes. I have advantage here, especially in terms of the eye shape. It produces a very high quality shape in terms of the iris, to reproduce the eyelids and to reproduce the eye image. Or you can apply the warp that is get the same pixels and apply some movements in the pixel until I reshape the eye. Okay, ideally here, in this case, it's better because in terms of color composition, I can see clear that I keep like the same color in terms of the eyes, in terms of the skin color, it's gonna keep like the same. Like 2 years ago, I started like my project by apply one systematic review. And I found like these papers, and these are the papers that fits better with our needs when we think about executing for edge AI. And my paper, my model, it was inspired in most of these techniques, and the techniques itself here are inspired for each other because the composition from the model is basically the same, sometimes CNN, sometimes UNet, but you see it's slightly different, but it's always basically the same step. One encoder, one generator, one warp, and in the second step, the color composition, because I need to correct the color to bring back my eye image into the final result. In terms of the Jabra gaze correction model for Edge AI, as I mentioned for you, the first step, it was think about the speed. I need to process one image in real time, not only one, but at least two images, as I have the left and the right eye. This should be executed in real time. Otherwise, it's not going to be a useful, or it's not going to provide a good user experience for our users. The second one, it was the eye shape, because I need to reconstruct the eye, but keeps the same shape in terms of iris, pupil, eyelids, okay? And this one, it was the best provided by the GAN. The third one, it was the color composition. And this was the fight between the GAN and the warp, because GAN provide for me better eye shape, and warp provide better color composition. Why I selected warp? Because the result, in my case, I need to cut the eyes using like Mediapipe to identify what are the eyes located. When I cut it and process and come back, you will see some exactly the window that it was cut, all this area here, then it was quite strange, although the quality, it was quite good. When I only compare like the image, the input image and the processed one, you didn't see any difference. The difference appeared only when I returned back to the original face. Then because of this, I decided to use the warp based. In terms of how to build my gaze correction model, I started by defining one data set. There are data sets available, but as we think about using in a company, I needed to produce my own data set, and it was a data set using synthetic and also real images. Then it was a long study comparing different implementations in terms of GAN and warping. Then I decided here that the one that we are going to use in our cameras, it is the warping based. Okay, then training with the PyTorch Lightning and using DVC to control the training process. And these are the two last steps, the one that I'm going to show to you. It was the optimization before, and now you will have the opportunity to test this because I deployed it in both cameras, the Luxonis and also the Jabra camera. Okay, the data set I used, I'm not sure if you know this tool. That link is for the tool, it's not for my data set, but I have generated here 1.5 million images. Okay, then it's combination. I create one specific user, like, then I move the eyes for 100 position and repeat this process until I achieve 1.5 million images. The second data set, it was a collaboration between Jabra and IFSP, it's Federal Institute of São Paulo in Brazil. Then we collected data with 208 people. And the best here, because Brazil, we have diversity, then we had a very huge diversity data set. I don't remember how many frames, but it was like 208 using two cameras, looking for 35 position around the screen, plus 2 times each camera. And yes, collecting data for like 2 seconds. Then we had a very huge one and use images in full HD. Then this is a high data set, and I'm working on this paper, and I'm gonna publish this paper, and the data set is gonna be available, okay? Of course, think about privacy here. I'm gonna also provide like information about the face, because basically you can have some interpretation what happened with the user face. But the practice here, the most important, at least for my application, are the eyes region. Okay, and all the annotation is gonna be available for you as well. I explained this before. This is the pipeline. If you compare with most of the papers, there are slightly difference because some use the anchor map, and then anchor map is basically get landmarks around the eye leads to define a new layer from your input image. Some of the some papers use the encoder, others prefer to get the X and Y and create the tile to repeat these until concatenate with the original image. You will see that there are slightly difference, but in general, like the architecture is gonna be the same. Only two more slides. These are some videos during my development process. And as you can see, you can compare the left one. It is the one where I changed the eyes, and the second one here, it's the original image. And as you can see, most of the time, the right one, it keeps like the eye contact. Of course, it's not the same quality as Maxine, but please consider that I'm execute this in camera, and this is a lower resolution image, okay? I can also combine with different models that we have in the company, like purification. Okay, I can get like apply the gaze correction plus the purification. Although my mother say that the left image is more beautiful, I cannot consider this, but let's see. You can see that I'm younger in this image. We have different models that we can combine inside our experience, okay? The next one, Elizabeth.
Yeah, it will be a rush presentation as they talk a lot. I need to go faster. Yes. And in general, when we talk people about hand gestures, they are a bit skeptical because normally they think it's only for games or something like that. But as we can see, we have some global reports that show this is a really huge market that is growing faster and a lot. Then maybe it's something good to think about. It's to develop something regarding hand gestures, recognition, and also tracking. According to the reports from these companies, the market is growing most because of the Internet of Things device, and also because of the improvements from artificial intelligence and machine learning models that, as we can see, we can deploy also for Edge AI, and it opens a really huge market to develop new ideas in new products. The main segment is still in human-computer interactions that cover, actually cover almost all the products in general, but virtual reality and gaming is also two big markets to explore. Then why hand gestures? Hand gestures are everywhere, not only in virtual games and virtual reality. We can see different applications from the consumer, from people, personal devices, even for the big industry. We have a huge of hand gestures applications for really serious applications, let's say, something like that, not only for entertainment, then also from new automotive, for example, using for interaction in general. It's something that is really new and it's growing. Here I bring some, I find some examples of some commercial applications. that uses also hand gestures or gesture recognition or gesture tracking or hand tracking that we can see on market. I don't know if you know all of them, but for example, my next acquisition probably will be this selfie drone that is one thing to have. And it's very interesting. It works with hand gesture recognition, only just not for control the camera, but to start the process of using the drone to run away and also to take pictures. Then we have tracking, also recognition. This is another example of an interesting product that uses hand gesture in commercial products. The best thing about hand gestures, I think it's that because it supports multimodality, that nowadays is something really important when we can integrate with other input methods. For example, we can integrate hand gestures with voice or with eye tracking and have a more versatile product when you can integrate those different kind of interactions. Then with multimodality, we can start thinking a bit more and exploring the perceptual human interaction, as Fabrizio told something about. That is when the environment or the devices are really perceptual with the human, what they are doing, what they need, what's next, like contextual environments. And it's something really interesting. The hand-based technology in general can be described normally in three kinds of functionalities, depending on the application, the needs of the application, what you can do. You can use only hand detection. That can be enough for some kinds of applications, for example, museum interactions for panels, this kind of stuff. Or you can use hand tracking when you need to follow up the movement of the hands, what they are doing, or like manipulating some kind of 3D objects, this kind of stuff. Or then use the hand gesture recognition that is regarding to the gesture itself, that can be a pose or a command for something that happens in the interface. Or you can combine more than one of those functionalities, let's say like that. Bringing the pipeline process from the literature, of course, with a bit of creative liberty here. Some steps could be grouped or understood in different ways, but here we can have a bit in general how the hand gesture recognition process occurs in a normal application, like not exactly from Edge AI, but we will see the differences from our general process from the Edge AI in some minutes. Then, for example, from the data acquisition for interface feedback, it can run in the same computer or the same system, or it can be distributed in different ways always depending of the application. I think is the best thing to describe any kind of system presented here. Then looking at the steps, the data for hand gesture recognition can be obtained from different types of sensors, and that can be for applications like with hand gestures for static gestures or for dynamic gestures. My focus is more on video-based application, as my research is applied to Jabra collaboration products as well. And like for professional cameras for virtual and hybrid meetings, I'm trying to discover different ways of interaction with functionalities of the camera using hand gestures. Then I will use like the recognition of the gesture pose. It could be static gesture or can be a dynamic gesture, on depending of the which kind of action I need the user performing on the camera. We are exploring this right now. The preprocessing for image-based applications will follow some different steps depending on the application. We can have here some suggested steps. that can be applied, like different techniques to reduce the process time and the costs for the next steps. Probably, normally we cut the image or resize it or identify the shape, this kind of stuff, to the next step be processed. Then the future extraction step involves identifying and extract different attributes from the data that will be different according to the sensor and what you are doing with the processed data. Then here I see some common libraries or frameworks that are normally combined together to extract this data according to the needs. Probably the well-known here, I don't know if someone works with hand gestures in general, it's Mediapipe, not only for hand gestures, but also for the body in general, that uses geometric, for example, to identify the pipeline of the hand gestures, the hands in general. This step is where the inference happens, that a prediction, classification, or a decision, it will happen according to the unseen data inputs that will be processed. Some frameworks are more recommended to static gestures, and others are more related to the dynamic ones. And this step of inference model will be in different location depending on the application. In edge AI, it will be on device, or in regular application, it can be in a server, or it can be in a cloud, it depends of the application again. Yeah. The post-processing and gesture interpretation can be refined after the inference, that the result can be like reclassified, or that can be mapped in final actions or final commands in general. Last but not least, here is the feedback step that is what the user is expecting. In user head, it's what they paid for and what they need the best feedback ever. Then like this is the important part. Normally, it's another kind of team, not the developer team, that thinks about the user experience, the user interface, the user interaction, and the result process, how it will be showed to the user. But this is a thing here that it's important to think. And regarding to hand gestures, it's important to show to the user what is happening, if the gesture was recognized properly or not, because sometimes the interface can be a bit stressed for the user. Here, just bringing in everything to the edge, what happens, probably in this part, the data acquisition and the interface feedback, it will be all together, different of cloud AI or another kind of developing using servers, for example, local server or wherever. How the steps are distributed here, then the same at the same place, and this is how it works. In general, it will be dependent of the camera itself, how is the power of the camera and all the characteristics that it has, how we are going to divide it. Sometimes it's better to use a kind of distributed architecture, not exactly cloud AI, but we can like develop in different steps. Much progress has been made in general about hand gesture recognition over the years, but some technical challenges still remaining. For example, the data set's not a problem, but I think that will be more a challenge itself. That is something hard to get new data. Even now, because of GDPR, as you know, it's hard sometimes to get new data that is focused on the application you really need. It's hard to get this data to training a new model, for example. We can see a lot of different data sets available from the internet, but normally they will not cover exactly what you need for your application. Then probably it's something that is really hard to work with. It's found in new data. We have some collaborations with the Institute of Technology from São Paulo to collect also a data set of hand gestures for this research, because in general, I'm working also a bit related to which are the best gestures for the application. Because when we talk about hybrid meetings, for example, it could be works very well in general, the processing, etc., the edge model. But if the gesture itself, the pose, I mean, is not a good pose for all the people that I'm going to. It's not a good choice for example, to apply. Like we have people from all around the world interacting at the same meeting room, for example, and it's something related to, okay, this gesture has a meaning for me, but for people from another region, there is another meaning. Then doesn't matter if I have a good designed process for Edge AI, and if the interaction process was not well thinking about, when I think about the vocabulary of hand gestures that I'm going to apply. Then the gesture vocabulary is nowadays a problem when I think about it. There is no standard about hand gestures in general. For example, you can see different kind of devices doing the same action, but one brand uses one gesture, for example, this one, and another brand can use these gestures for the same action. Then this is a huge challenge. Like propose, my intention is like propose a kind of study that can create some standard regarding vocabulary appropriated for this kind of products, for meeting rooms in general, Jabra, for products from collaboration. Because of course, the gesture set depending of the context also, depends of the application, depends of the device, but also the context of use. And we are going to discover this kind of standard, if it exists or not. How does it work? And why this is a problem? Because, and this is hard to solve, it's because we have a cultural problem, not a cultural problem, a cultural characteristics between people. The people know something that they are learning from another device. Sometimes they know something that they watch in a movie. Then this kind of stuff, it concords with the cultural that they have created with. And when you think about the cultural, is not related exactly to the country exactly, you know. There are a lot of characteristics that count in this prism of cultural, meaning, interpretation, etc. Then another thing related to the cross-cutting problems, that is a kind of transversal challenges, is how can I discover that the user is understanding that gesture, that they are going to use in the best way, that you have a good interface with that gesture. Sometimes we think that we need to count with the user intuition, but sometimes it's not enough. Sometimes we need to educate the users about some gestures. Then probably in general, in my area of actuation, that is human-computer interaction, more related, it's really, we expected that you can count with the intuition of the user, but sometimes it doesn't work at all. And because of this, the fluidity, that it's like the flowing about the user, even more related with the modality, when you can use it, combined characteristics, combined modalities of interaction at the same, the fluidity, like it's needs to work properly and really natural in between for the user. It's something really hard to reach. Maybe you have this experience with something related. Then for those who want to get a look, I have applied Edge AI in a camera that is this one. It's Luxonis 1Max, that is the same architecture from Java, the same. And we use the Myriad Explob format because actually it's a model that is still available on internet, and it's already how can I say, condensed and properly applied for the model. And we use the Mediapipe as palm detector and landmark. Then you can try after the section, all of them, actually. Yeah, that's it. Now, Shan.
How are you guys doing? First day of CVPR and it's already 5:40. I hope you still have energy for one last section. So I'm going to be focusing on sound as a modality. As they mentioned before, at GN, we are trying to look at multimodal perception and how the people at the far end could feel like being in the same room as where the camera is recording. And that's where we are looking at audio or sound as a modality. So what is the motivation behind it? We have the video, we have an understanding of what the person looks like on the camera, but we also want to know who's speaking at what time. And if it is a bigger room and a lot of people are speaking at different times, the person speaking last is given as much importance as possible. And that's wherein we are using modality of sound to make sure the person who's speaking is given as much importance. And to do that, today I will talk first what sound is as a modality and what are the different audio features. As it is a computer vision conference, I will explain the different features that are commonly used in audio, and then show you a completely audio-based model that we have deployed on our Panacast P50. And as well, I will also show some purely multimodal models that we are looking into. So what is sound? Sound is produced by vibration of an object. As you can see in this, as you can see in this small animation that I've created, the air molecules that are oscillating over time, that creates this compressions and rarefactions. And this is a simple animation of what it looks like as a sine wave. So this is basically sound, and it needs a medium to propagate, and that is air. Now, how do we, as you can see in the video, animation before, it is a continuous system. It is a analogous, sound is analogous. But when we have to do it on a digital domain, we have to do it in a digital way by not being continuous, but discrete. And that's where sampling comes in. Sampling is capturing and converting audio signals basically into a digital domain. And it is quite similar to, I would say, how pixels, more number of pixels in an image gives better quality. Similarly, higher sampling rate or higher sampling gives a better quality audio. Now, this is a simple representation of an audio in the time domain as well as in the frequency domain. As you can see, this parts, those are where the amplitude is increasing, and when it's there's no amplitude, it's a flat line. And this can be converted into the frequency domain by a simple mathematical function called the frequency fast Fourier transform. And this is the representation in the frequency domain. So now we have time, we have in the frequency domain, but still in reality, we need a continuous. We know when the frequency, what the different kind of frequency is available at a particular time, but we don't know how it is changing over time. That is where we create these spectrograms. So spectrograms is basically a representation of audio in a time frequency domain. So we have the full waveform over here. What we do is we divide these into chunks, and each chunk is a frame. And that frame is similar to how you have in video. So we have different frames, and you choose the frame size. And then next thing you do is the windowing. So now that you have a chunk like that at the end, you window it down so that there is less spectral leakage. And then you decide whether you want to jump completely or how much overlap should be there between different frames. And that is the hop size. And finally, you get this image at the bottom, which is a representation in the time frequency domain. But perception of sound is quite different for humans, as it's shown. For example, if the frequency between 210 kilohertz and 220 kilohertz is not easily understood by humans. Is easily understood from 200 to 210, but from 2000 to 2010 is not that easily understood. This scale change in sound is quite logarithmic, and it's not really perception of sound is quite different for the human ear. So that is where we use something called as a MEL scale, which converts the whole spectrogram into a MEL filter banks, and then also does a logarithmic scale on it, and we get something called as the log MEL spectrogram. This spectrogram is using a linear scale, and it's also using MEL scale, which converts a spectrogram. And if you can see on top, I have the spectrogram, and down is the log MEL spectrogram. As you can see, because of that, we can have a much better representation in the lower frequencies and better understanding as humans, because the logarithmic scale is taken care of. And now this gives more information, and it is obviously our models can understand better the representation of sound. And then the next step is, once we have the log MEL spectrogram, and another feature that is commonly used nowadays, especially in speech recognition, is MFCCs. So it is, once you have the waveform, you get the log MEL spectrogram, and the next you come to the discrete cosine transform, and then you get an MFCC. What MFCC does is it's very good at representing your vocal tract and especially your speech. And that it also reduces dimensionality quite a bit, that only the important parts of the whole log MEL spectrogram is remaining. And that's what helps the models learn better about speech recognition. That's all fine and dandy, right? But we have a lot of these mathematical concepts and mathematical stuff and the transformations. But how do we do that? That is where this package of Librosa comes in. You can think of it like OpenCV, but purely for audio. You have librosa.load, similar to cv2.imread. You have the whole displaying of a wave show is as simple as a single line. And you can also get the whole MFCC just by librosa.features.mfcc. You don't have to do the whole spectrogram, log MEL spectrogram. All that math is dumbed down into one single line of code using Librosa. So now, this is the one model that was deployed into our Panacast P50 model, which is purely audio-based. The original model was taking azimuth is this angle like this, and elevation is like this. So what we have is a 180-degree field of view along the x-axis, and we divide that 180-degree field of view into 37 different parts. And from -90 to +90, we have all the divided into resolutions of 5 degrees each. And that's how we get to see if a sound is coming, we have two different probabilities. One is to see if it's speech or not, and probability to see which part of this resolution is the sound coming from. And for this, I explained the different features because over here we use spectrograms, and this was what was used for training the model. And now this is the next model that we are looking at. Now, this was the previous one was completely audio-based. So this is sound localization, which is using both audio and images. So this is the paper which we are looking at. It has an image encoder for clip and audio encoder called wave to clip. And what it does is the embedding, it is put into a single embedding space, and it learns how to put the similar pairs into closer and the non-similar pairs more further apart. And that's how contrastive learning is used to see where the sound is actually coming from. And this one uses raw audio waveform. 1, 2, 3. This is a test. 1, 2, 3. As you can see over here, we are looking at where exactly the sound is coming from, and what are which even the snap of a finger can be localized, and we get to know, okay, this is the area of interest from where the sound is learning from, and it's a completely end-to-end model that is learning this contrastive way. But now we need a more different approach. One of the big difficulties we had with our DOA was the further away the people are, then the resolution is smaller. It makes it more difficult to see who's speaking at what time. We already have an inbuilt model which Anuj helped with the head body detector. So from that head, we get only the cropped faces of the head, and we get the audio input. We convert that into MFCCs, and we have the visual encoder and audio encoder. And together, we can get an active speaker detection. We can see if this person is speaking or not. Hello, 1, 2, 3, checking. Can you hear me? Can you localize? Hello. So this, as you can see, is better at seeing speech, because the MFCCs were used and the lip is being used to be able to see if the person at present in the bounding box is talking, is doing active speaking or not. This is from one perspective. That was, both of these videos were taken in the Panacast P20. Now I'll show you a video which was taken in a video P50 with a lot of people present in the room and people talking.
But it's a one-to-one. Yeah. And if I am not mistaken, I think the cost or something like it's in thousands, right, to do the whole thing. But it is a good experience. But how long would it take them from being a one-to-one versus a group-to-group? Yeah, we had an opportunity.
So that was a brief demo of the active speaker detection that we have been looking at. And yes, so this is more in the next pipeline, and hopefully similarly, we'll be having this deployed in our next products, which we'll be hopefully showing next year or so. And we have, after this, the demos and questions we can take, right?
Yeah. Thank you.
Okay.
Then, in fact, it's only to finalize here in terms of demo. We're going to set up now at least these 4 demos. The gaze correction, where you can test here, body segmentation, hand gestures, recognition, and also the sound location. It basically will have all the time that you can try and test and ask more questions. It's only one small information regarding to the Jabra collaboration business. As you saw, we are different researchers, work in different projects. We sometimes collaborate with each other, but we have one specific project, each of us. The moment that we finish the project, we get the module, the best mod that we have, and we deploy for this experience. Then the experience, sometimes we don't have a consensus inside Jabra. If the name is XP or XPy, then we still decide, but I usually name this as XPy, and the XPy is basically one experience. Once you have the module, one interaction module ready, we create a filter. And this filter, as you can see, it's a pipeline similar to the one that you saw in the camera. Then it's only connect, like, as you can see here, this is the person segmentation. This is the one, it was implemented by Narcy. Then it has some input and output, and we can combine different interactions. Then I can also demonstrate for you this, but this is not public. This is a private use in our Videotech. At least our market team can use the experience that we implemented to have meetings with other companies. Then, in fact, as I said, we're like 24 minutes behind it, but now we have plenty of time to answer your questions. Okay, with regard to the second part of this presentation.
Or the first.
Or the first. Yeah, or the first. Yes, feel free to ask a question.
Already.
Yes, sir.
Where is the need for review transformation? What to go
So what we want the model to learn as much as possible from the audio features, and that can be done by mimicking the human perception as much as possible. So logarithmic human pitch, we perceive pitch on a logarithmic scale, whereas the Fourier transform is on a linear scale. So converting that into log MEL spectrogram helps understand better in that for a human perceptive level, and having the features in a human perception level helps the model also learn better. I mean, whatever models and stuff that has been trained on, it has been shown that the better features or better, especially with speech recognition, when you get MFCCs, the model learns a lot better and the performance of these models are also improving. So it depends on your use case. So I'm explaining the difference between spectrogram, log-MEL spectrogram, and MFCCs, but all features are used for different models. For example, we used only spectrograms on our DOA, but MFCCs was the use for the active speaker detection, and raw audio waveform was used for the sound localization. So it depends on the use case in itself. But because speech recognition and the talking of a person is much more best mimicked with an MFCC, that is what is used. In the sound localization one model you're asking, yeah. So the image encoder has the embedding space, and the audio encoder has an embedding space, and the contrastive learning, they brought all the embeddings are brought into a mutual space, wherein it is learned to differentiate between by contrastive learning to say, if it is me talking and my voice, then bring those linearly closer using cosine similarity, and if not, bring them further away using cosine similarity.
And if you have a wonderful thing, I guess it wasn't clear, especially I forgot to mention this for you guys, but you saw the perspective of the video here. And the video packet is quite small. It's of machine learning for audio. The noise reduction is sound localization. Then the key in Jabra for using machine learning to improve the audio, it's really big. We have a very big number of research work with the audio perspective. Okay, we offer like, because Shan works directly with us, we basically hiding into having our video tech the perspective of the audio, but we have a very big team that specifically use machine learning and neural network models to improve the audio as well.
Maybe I can add
the camera's perspective and also.
Yeah. For the audio, I can add a little bit. So the model architecture that you saw, there was a video aspect of that. There is a video encoder. That's basically a clip encoder. Given an image, you get a certain kind of embeddings out of that. Then you have an audio encoder. Given an audio sample, you get a certain set of embeddings. Now we apply a cross attention layer on top of that. So what that does is basically it's attending to both audio and the video features in sync and trying to figure out that where the audio is coming from. So it's basically trained end to end like that. So that's how you can get both the person location as well as the audio information, combine them together and learn and attend to both of those. And then based upon that, you can say, okay, the audio is maybe coming from here. So that's how the training was done for that.
So I guess, like, if I'm understanding this correctly,
saw a video where you had the heat map as to where the
Yes.
spectrum is. That inference is actually based on your video as well as your audio.
Yes, both the things are both the things are in parallel. You require both audio and video.
Yes.
Another information share solved the one problem because 2 years ago we tried to identify for the speaker only based on the Higgs movement. That was it was our limitation. Why? Because we can build like the platform without needed to click. And why only use the Higgs movement? Because you can have like the sound, someone in the background talking, knock at the door, any kind of situation. And if I use it only the sound channel, I couldn't have this noise in the moment that I'm gonna take it. However, we didn't have good performance in terms of the Higgs movement because still it's only part of like analysis and the input that preparation regard to that is quite difficult. Another thing that we tried is still something one challenge for us is like predict the moment that people is going to speak. How much it takes? Now it takes almost 1 second, but we'd like to reduce these for let's say 10 milliseconds, or even when the leads start for one speak, not for only normal movements, then we can also have this analysis, and it depends on the perception as well. Watch and make it's basically remove like noise that doesn't come from the face, and like that heat map provides to us the possibility to analyze the video and all the perspective to create this automatic and muted system.
Yeah. So another issue with the lib-based system is that if you are just sitting in the front of the camera, you have plus minus 30-degree field of view where it will work. After that, you lose the lip landmarks. So it won't be scalable.
I have one question with the audio encoding part. Like you have a video encoding and an audio.
Yeah.
So in the presentation, showing that you are encoding the azimuth and the elevation.
Yeah.
So
No. The original paper does azimuth and elevation. In our model, we are doing only azimuth.
Yeah.
Only azimuth.
Only azimuth.
Okay,
Because most of for us use cases, everyone is more or less sitting. So we don't, elevation does not recreate that much of a difference. It's all mainly azimuth.
So what do you mean by when you say you are using the azimuth? So you have a microphone, like one microphone?
We don't have one microphone. The Panacast 350 has
And
8
microphones.
That's what it was the first line which I think I didn't mention. Okay. So we are getting spectrograms from all the microphones, and they are distributed in a line.
Yeah.
And we have the azimuth from -90 to 90 degrees. And we have divided into 37 sections with 5-degree resolution each.
Okay. So these 8 microphones are giving you the feedback from which you're able to estimate that.
Yeah.
Yes.
Goes into your.
Yes.
And even on the microphones, you have beamforming and stuff happening. So it helps with the better voice pickup and reducing background noise and things like that. So that makes it more cleaner before pre-process.
You know, to calibrate that. So.
Yeah.
And the output from the spectrum. So just trying to know how is the pipeline tension what we need to achieve after machine learning to that.
I mean, in the end, it is similar. If you see a spectrogram or a log-level spectrogram or MFCC, in the end, it's like an image, right? And we have temporal aspect because we are getting each frame, each spectrogram of each frame. So in the end, how you would do with computer vision for image or for a video, it's a similar pipeline that would be for audio as well.
So basically, once I convert my audio signals from raw audio to FFTs to mil spectrograms, it becomes like an image that captures both the time and the frequency domain, as well as the harmonics that you see as the high and low level values. Now it becomes like an image classification problem. Now I can train like a simple convolutional neural network to classify that what this audio is, for example, bird versus human versus something else, or some other kind of things. And I can use it in regression, classification, other kind of tasks. So it becomes an image classification problem or image regression problem, basically, instead of a time domain based, frequency domain based thing. That's what this is helping us with.
So I'm trying to correlate it to my research.
Yeah.
Researching on spectrum sensing cognitive behavior. So I'm trying to analyze. So if I can apply machine learning, I'm trying to convert it first to spectrum.
Yes.
I need to do?
So just whatever Shan told you here.
What I'm interested in this one.
Yeah.
Yeah, I have now. Trying to plan to finish my work and I
So whatever Shan told you in terms of the presentation, the steps, it's basically what you have to do. Same thing. Yes.
You were mentioning something about how you the cheap weight like in a process.
Oh, glass walls? Yes.
How should you be able to announce it?
Okay, so so that is still patent pending, but okay. It's basically a simple kind of an algorithm. We can't run depth model or anything. So basically what we are doing is, in a very naive way, what you can do, I'll tell that then. If you know the bounding box sizes and if you know the ground truth distance kind of, so based upon that, if you have different people at different distances from the camera, and if you know the bounding box sizes, you can collect that data and you can train as simple as a linear regressor, and that will give you the estimates of where the people are. And now for each of the people who are outside the boundary, you can tell that, okay, this is above the distance from the camera and reject them. So basically it will eliminate, like move them out of the boundary. In very basic sense, that's it. It's a little bit more complex on the system, but it's patent pending, so I cannot talk more about the details yet.
We have to close.
Sorry. Yeah, so we are analyzing depths, but that's like a offline parameter. We are not running any depth model. We don't have the compute on the existing ones. It's an offline process.
If we can have one last, I think the guy is asking us to vacate.
To leave.
I'd like to stay here.
But we are here.
It was surprisingly much to leave. But let's be fair.
Our cameras work on USB laptops. We can just put it outside.
Yeah, we can find. Yes, please.
Yes.
Question concerning the person you take. Could you elaborate how you make use of the temporary consistency with an additional loss term, or you just ensure that the output for every frame is equal and stable?
No, the loss remains the same. It's just that how you pass in the data set. So in image-based processing, your input dimension is NCHW. Now, batch size, channel, height, and width. Now, when you have the temporal aspect, it becomes NTCHW, where you have the timestamp, which is the number of time frames that you're taking. And then during model training, you multiply T and N, and that becomes your bigger batch size. And that's how you feed in frames continuously to train your GRE model layers. Yeah. For just the GRU layers, but it trains the whole model like that then. On videos, if you have to train it on videos.
Okay, thank you all. Yes, for be part of this, we're very satisfied with the final results. But to have more questions, we will be here outside and let's see how we can manage this. Thank you. I will upload today. Yeah, tonight in our website. It's gonna be there. Yeah. Okay, thank you. Thank you.
Like a very but if your backbone is bigger and can take more of the inputs until you reach the output, it's still very, yeah. On average, it's legit. On average,